I always liked mathematics, but I was wondering, is it possible to learn all of mathematics? Hey guys, welcome back to my YouTube channel. This might sound crazy, but I'm going to be doing all the math courses at Rutgers University in New Brunswick. I'm going to be doing all the undergraduate and graduate level courses. So for undergraduates, this includes all the 100, 200, 300, and 400 level courses. And for graduates, includes all the 500 and 600 level courses. And if you didn't know, Rutgers University in New Brunswick is a diverse school. So that's why they have other math programs, not just solely on mathematics, but also in applied mathematics and financial mathematics. And I can remember the course code number is 640 for just mathematics or pure mathematics at the graduate level. And for applied math, its course code number is 642, and financial mathematics, it's 643. But this is something I've been really interested in sharing with you, and I wanted to show with you and learn what I know since I like math. And also in the video, I'm not going to share and do any of the seminars or research courses because on their website, it's not that important. But for now, I'm going to also use a whiteboard to do my work and show with you what for every problem, and a marker right here. This is a black one I chose. So basically what I'm going to be showing you is one problem from every math class at Rutgers. I found everything. I'm so excited to put it on this video and share it with you guys. So without further ado, let's get into it. Alright guys, so we're trying to solve 4/5 times 3/4. What I can do here is I can multiply the numerator. So 4 times 3 is 12, and 5 times 4 is 20, and 12 over 20 is reduced to 3/5. Solve for x. So we have 3x minus 5 is equal to 2x plus 7. So let me rewrite this. So we have 3x minus 5 is equal to 2x plus 7. And what I need to do is I would need to get x by itself by subtracting 2x to both sides of the equation. So let me subtract 2x here. This cancels. We have x minus 5 is equal to 7. Now I could add 5 to both sides to get x alone. We have x is equal to 12. Alright, in this problem here, I'm trying to solve for x. So we have 3x plus 2 over x minus 1 minus 2x minus 3 over x plus 2 is equal to 1. So let me rewrite this. And all we do is need to find a common denominator. So here I'll just basically multiply by x plus 2, here x minus 1. And then work with the top. We get 3x squared plus 6x plus 2x plus 4 minus 2x squared minus 2x minus 3x plus 3. Let's do more simplification. Now, I can simplify even further here. And this would be plus 13 plus 1 over x minus 1 times x plus 2 is equal to 1. Now I could just multiply the denominator by x minus 1 times x plus 2. So that would give us x squared plus 13x plus 1 is equal to x minus 1 times x plus 2. And expanding the right side, we get x squared plus x minus 2. And I like to subtract from both sides. Also this. And add 2. So this will cancel. That will cancel. That will cancel. So we have 12x plus 3 is equal to 0. Now let's just solve for x. There you go. So x is equal to 1/4. A city park has a rectangular garden that is 60 meters long and 40 meters wide. The park administration plans to build a walkway of uniform width around the garden. If the total area of the garden and the walkway is 4,800 square meters, what is the width of the walkway? So basically we have to figure out what the width of the walkway is. So let me also denote that W is the width of the walkway. And also let me write down the length, which is 60 plus 2W, and the width is 40 plus 2W. And let me show you a visualization here. So this would be like a rectangle, and you would have the length right here would be 60 plus 2W, and the width would be 40 plus 2W. And we know we have to find the area first. So let me write down the area. So the area of a rectangle is length times width. And we know that A area is 4,800. So that would be 60 plus 2W times 40 plus 2W. Let me just expand this. Do some more simplification. And let me subtract 4,800 to both sides. Right over here, we have 4W squared plus 200W minus 400 equals 0. Then I would divide by 4. So it would be W squared plus 50W minus 600 is equal to 0. And now I would use the quadratic formula. So it would be W is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. And A would be just 1. B would be 50. And C would be negative 600. And now let me just plug in the formula, the numbers in. So let's see, 50, we would have negative 50. We will have negative 50 here. Plus or minus square root of 50 squared minus 4AC all over 2A. And if you simplify from here, we get negative 5 plus or minus the square root of 400 over 2. So even simplifying from here, we get negative 50 plus or minus 70 over 2. And we can see we will have two solutions, which gives us that. So let me see. So we would have W could be equal to negative 50 plus 70 over 2, which is just 20 over 2 is 10. W would also be negative 50 minus 70 over 2, which is negative 100 is negative 60. So we have two solutions. We have 10 and negative 60. But a lane cannot be negative, so W has to be equal to 10. So the width of the walkway is 10 meters, since a negative width cannot be negative. A fair six-sided die is rolled. What is the sample space of this experiment, and what is the probability of rolling an even number? So first, let me write down the sample space, which is a set of all possible outcomes. So let me denote S. Since it's a six-sided, it would be 1, 2, 3, 4, 5, 6. And also rolling an even number, which would denote as E. So in this case, we would have 2, 4, and 6. And basically, I would denote the probability of rolling an even number would be on the numerator would be rolling an even number over the total outcome. So this would just be E over S, which would be, so we know that E is 3 and S is 6, so that would be 1/2 or 50%. The probability of rolling an even number is 1/2 or 50%. Tim invests $2,000 in a savings account that offers an annual simple interest rate of 5%. How much interest will be earned after 3 years, and what will be the total amount in the savings account after this period? So first, we're trying to figure out how much interest he will earn after 3 years. So first, let me denote P. So what's given is we have 2,000, which is the principal. We have R, which is his annual interest rate, which is 0.05, which is the decimal. So annual interest rate. We also have T, which is his time is 3 years. And the interest. So it would be I is equal to P times R times T. And using the formula for simple interest. So basically, let's plug in what we have. So we know that P is 2,000. And we know that R is 0.05. So I would be 300. So Tim will earn 300 in interest after 3 years. Now we have to figure out what will be the total amount in his savings account after the 3-year period. So let me write down. So it would just be A is equal to P plus I. We know that the principal is 2,000 plus 300. So A is just 2,300. We also put the $sign there. So Tim will have 2,300 in his savings account after 3 years, with 300 of that being the interest earned. All right, now we're trying to solve 1.3 plus 7.5. So let me write this column form. So we do 3 plus 5, which is 8, and 7 plus 1 is 8. So the answer is 8.8. All right, we're now trying to find the missing angle, which is x. So right here we have a straight line. We're trying to figure out what this x is, the missing angle. So I know that a straight angle adds up to 180. So all I can do is just do 180 and just subtract the 78. Bring down the 7 here, this would be 2. So x would be 102 degrees. Evaluate 3x plus y over 5c plus x if x is equal to 5, y is equal to 7, and z is equal to -3. So really simple, we just gotta plug in each variable. This would be just 15 plus 7 over -15 plus 5, which is just 22 over -10, which in this case is just -11 over 5. So our answer is -11 over 5. Let g of x equal the cube root of 3x plus 5. Find the value of the inverse of 3. So let me write this down. Now let me just try to solve for x by taking its cube root. By squaring it, we have y cubed over 3x plus 5. I can just subtract both 5 from both sides. Now we have x is equal to y cubed over 5 over 3. Now this would be, I can just write this as g prime of x is equal to y cubed minus 5 over 3. Now I just plug in 3 into this problem. This would just be 27 over 5 over 3, which is just 22 over 3. The inverse of 3 is 22 over 3. Find the values of the trigonometric functions of data if the terminal side of data contains the point 3, -4. So first off, I want to draw a visualization to show you what it looks like. So we have a triangle right here. We have x is equal to 3, y is equal to -4, and then r. So we're trying to find the trigonometric functions. So first off, I want to find what r is. So r is just x squared plus y squared. It's just the hypotenuse. So we have 3 squared plus -4 squared, which is just 9 plus 16. Then it will be 5. We have r is equal to 5, so we could just write down, I can write down the trig functions. So sine of data is just opposite over hypotenuse, which is just y over r. In other words, it's just -4 over 5. We do cosine data. It's just adjacent over hypotenuse, which is just x over r. So we have 3/5. Let me do tangent of data, which is just opposite over adjacent, which is just y over x. So it'll be -4 over 3. Let me do cosecant. Cosecant is just 1 over sine of data, which is really just 1 over -4 over 5, which can be simplified to -5/4. Let me also do secant. So that would be 1 over cosine data, which is just 1 over 3/5, which is just 5/3. And cotangent of data, which is just 1 over tangent data. It's just 1 over 4/3, which is just -3 over 4. I found all the trig functions of data. And we're trying to evaluate this function, log base 3 of 1 over 81. So let me write down a log property. And let me rewrite the problem. We know that 1 over 81 is equal to 3 to the -4th. So therefore, it would just be -4. Find an equation of the line tangent to the graph y is equal to 3x squared plus 1 at x is equal to 2. So first off, let me plug in 2 to find the point on the graph at x equal to 2. So this would just be y is equal to 12 plus 1. So y is equal to 13. So our point is 2, 13. Now let me find the slope of the tangent line as x is equal to 2 by taking its derivative. So y prime would just be 6x, and y prime 2, just plug it in, would just be 12. And now let me write the point slope form of the equation of a line. So let me do y minus y1 equals m times x minus x1. So this would be y minus 13 is equal to 12 x minus 2. Doing simplification. And solving for y, it would just be 12x minus 11. So this is the equation of a line to the graph y is equal to 3x squared plus 1 as x is equal to 2 is this. Y is equal to 12x minus 11. Consider the graph of the region in the first quadrant bounded by the curves y is equal to x squared and y is equal to 3x. Use the method of washers to set up the integral whose values is the volume of the solid obtained by revolving the graph about the x-axis. So first off, let me draw a graph to show you what it looks like. So that would be y is equal to 3x, and then a curve shape right here would be y is equal to x cubed. So this point right here and this point right there. And it would be shaded in like this. And then 3 would be right here, and then 9 would be up there. And let me just set up the integral. So v is equal to pi of 0 to 3 of 3x squared minus x squared squared dx. Now let me solve this integral. Let me bring out the pi. Let me work with the integral. Let me plug in f of 3. This would be 3 over 27 minus 243 over 5. Which is just 405 over 5 minus 243 over 5 is just 162 over 5. And let's figure out what f of 0 is. It's just 0. Let's see, 162 over 5 minus 0 is 162 over 5. And we can't forget the pi, so it would be 162 over 5 pi. So the volume of the solid obtained by revolving the graph about the x-axis is 162 over 5 pi. Find the derivative of x cubed times inverse of secant of x cubed. So in this problem, we're trying to find the derivative. And this is an example of using the product rule. So first, I would take the derivative of x cubed, which would just be 3x squared. Then leave the first alone. Then work with the next function. So it would be the derivative of inverse secant of x cubed would just be 1 over x cubed of x to the 6 minus 1. And then we also have to take derivative of the inside, which is just be 3x cubed. We see that these will cancel. So simplifying from here, you get 3x cubed inverse secant of x cubed plus 3x squared over x to the 6 minus 1. Find the Taylor polynomial for the function ln of sine x at a is equal to pi over 2 up to the 4th degree. So first, let me write down f of x is equal to ln of sine of x. And let me take the derivative of ln of sine of x, which is just be sine of x times cosine of x, which is just really cotangent of x. Take its second derivative, so that would be negative cosecant squared of x. Take its third derivative, which would just be 2 cosecant of x times cosecant of x minus 2 cosecant of x times negative cotangent of x times cosecant of x. We're using the chain rule. And this would be equal to 2 cosecant squared of x times cotangent of x. And now let me find the fourth derivative, which would be 4 cosecant squared of x cotangent of x times cotangent of x plus 2 cosecant squared of x minus cosecant square root of x, which is just 4 cosecant x times cotangent of x squared minus 2 cosecant to the fourth of x. And now we can have sine of pi over 2, which is just 1. Cosecant of pi over 2 is 1. Cosine of pi over 2 is 0. And cotangent of pi over 2 is equal to 0. Now let me evaluate each. A is equal to 2 and 2 its derivative that I wrote down. Now let me write down t of 4, which is be pi over 2 plus inverse derivative of pi over 2 times x minus pi over 2 plus f derivative of 2 factorial of x minus x over 2 squared plus f to the third pi over 2 over 3 factorial times x minus x over 2 plus the fourth of x minus x over 2 to the fourth. Now let me just simplify this even further. So it would just be 1 over 2 of x over x pi over 2 squared minus 1/12 x minus pi over 2 to the fourth. So this is the Taylor polynomial for the function ln of sine of x at a is equal to pi over 2 up to the fourth degree is this. Given the equation dy over dt is equal to y squared minus 4, determine the critical solutions and decide if it's asymptotically stable or unstable. So first, let me write down the equation. Y squared minus 4 is equal to 0. Break these down into 2. Be y minus 2 plus y plus 2 is equal to 0. We have y is equal to 2 and y is equal to negative 2. So these are the equilibrium solutions. And we need to determine the stability of each equilibrium solutions. So first, we will have y is equal to 2. And determine if this is stable. First, let me plug in 2 times 2 is 4. And we can see that since 4 is greater than 0, we can see that y equal to 2 is unstable. Emily also check for y is equal to negative 2. So that would be negative 4. And we can see that since negative 4 is greater than 0, we could see that y is equal to negative 2 is asymptotically stable. Solve the system of linear equation using Cramer's rule. So we have these two equations, 2x plus 3y is equal to 13, and we have 4x minus y is equal to 7. So first let me write this. Let me denote x as a matrix. So we have 2, 3, 4, negative 1. And let me denote x here and b here, which is 13 over 7. So first let me determine the determinant of s. So it'll be 2 times negative 1 minus 3 over 4. And we see that the determinant of s would be negative 14. And now let me determine what x of s is. So basically I'm replacing the first column of s with this one. So it would be 13, 7, 3, negative 1. And using the determinant of this would be negative 34. And now let me determine the determinant of s of y. We get 2, 13, 4, and 7. Which is just negative 38. And now let me determine what x and y is. So for x, it would just be the determinant of x of x over determinant of s. And that would be, just plugging in, negative 34 over negative 14. And this could be simplified to 17 over 7. And let me determine y. So it would be determinant of s of y over determinant of s. And this would be negative 38 over negative 14, which is just 19 over 7. So x is equal to 17 over 7 and y is equal to 19 over 7 using Cramer's rule. Find the parametric equation of the line L defined by the vector function RT is equal to 2 plus t, negative 1 plus 2t, 3 minus t, and the point 1, 2, 1. So first, let me write down the directional vector. We denote this as d is equal to 1, 2, negative 1. And let me write down the parametric equation. The R of t is equal to P plus TD. We know that P is equal to 1 to 1, and D is equal to 1 to negative 1. We have RT is equal to 1 to 1 plus T of 1 to negative 1. So simplifying from here, we get 1 plus T, 2 plus 2T, 1 minus T. And now let me write down X, Y, and Z. It would be 1 plus T, Y is equal to 2 plus 2T, and Z would be 1 minus T. So let me write down as RT. So it would be RT is equal to 2 plus T negative 1 plus 2T, 3 minus T. So basically this is the parametric equation of the line L that passes through the point 1, 2, 1 and is parallel to the line defined by R of T is equal to 2 plus T, negative 1 plus 2T, and 3 minus T. We also write down the points around here too. Solve dy dx is equal to y times sine of x over 1 plus 3y squared, where we have y of 0 is equal to 1. So the first step I like to do is do this by separations. Let me rewrite this as dy dx is equal to y sine of x over 1 plus 3y squared dx. And basically, I would like to multiply this by dx here. So this will cancel, and we had dy is equal to y times sine of x over 1 plus 3 squared dx. And now I would work with the right side. So also let me write down 1 plus 3y over y dy. I'm just basically taking this function and moving it over to the dy side. So this would be sine of x dx. Also divided by y too, which I'm separating y and x. From here, I could take integral of both sides. So let me work with the y's. So we have ln of y plus 3y squared over 2 plus c1. And let me integrate sine of x dx, which is just negative cosine of x plus c2. And now I could write on both sides of the equation. And now let me plug in y of 0 is equal to 1. So we have ln of 1 plus 3(1) squared over 2 is equal to negative cosine 0 plus c. Simplifying from here, we get ln of 1 plus 3/2 is equal to negative 1 plus c. We have 0 plus 3(2) is equal to negative 1 plus c. So c is equal to 3/2 plus 1 is just 5 over 2. So basically we have ln of y plus 3y squared is equal to negative cosine x plus 5 over 2. Given the bond with the following characteristics: face value $1,000, coupon rate 6% annually, time to maturity 5 years, yield to maturity 5%. Find the present value of the bond using the given yield to maturity. So first, let me write down the formula for price. So we have PV coupons plus we also have the PV face value. And now first I need to find the annual coupon payment. So it would be the note C is equal to face value times coupon rate. And C would be 1,000 times 0.06, which is just 60. And now we need to find the present value of the coupon payment. So we have to find PV of coupons, and that is equal to, let me write down the formula. Now we just plug in and this would be 261.59. And now we have C is equal to 60, and we also know that R is the yield to maturity, and N would be equal to 5. So let me just write that down. So C is equal to 60, R is equal to 0.05, and N is the number of years. And now we need to find the present value of the face value. So let me write up here. Is equal to F times 1 plus R to the negative N. So that would be 100 times 1 plus 0.05 over 5, negative 5. And we have the value. We have the present value. It would be 782.01. And we figured out that. And now we need to find the total present value of the bond. Like just basically add the two. And I should get 1043.60. So the present value of the bond would be $1,043.60. Let g of xy is equal to x squared times y plus x times y squared plus 2x. Find all the critical points of g. So first, let me find the partial derivative with respect to x and y first. Let me denote g of x, xy. Basically finding the partial derivative with respect to x, so it would be 2xy plus y squared plus 2. Now for y, now let me set it to 0. And we see that for f of 0, we have so we have y squared is equal to negative 2, but there is no real solution. So let me also work with respect the partial with respect to y that I wrote. Let's set to 0. We take out an x. We have x is equal to 0, and x plus 2y is equal to 0. And now let me solve for y. Plugging the negative 2y in. This would be negative 4y squared plus y squared plus 2 is equal to 0. And this would be negative 3y squared plus 2 is equal to 0. And now let me solve for y. So we have y squared is equal to 2 over 3. And we can see that y is equal to plus or minus square root of 2 over 3. So let me write down y is equal to 2 square root of 2 over 3, which implies that x is equal to negative 2 times 2 over square root of 2 over 3, which is just equal to negative 2 square root of 2 over square root of 3, which is just negative 2 over square root of 6 over 3. And for y is equal to negative square root of 2/3, which implies that x is equal to negative 2 times square root of 2 over 3, which would just be equal to 2 over square root of 2 over root 3 is equal to 2 times square root of 6 over 3. So let me write down the critical points. And so these are the critical points. Given the differential equation dy over dt is equal to y squared minus 2y with the initial condition y0 is equal to y0, show that for each y0 is in 0, 1, there exists a unique solution of differential equation with the given initial conditions. So the standard existence and uniqueness theorem for ordinary differential equations required the function f of y to be continuous in y and satisfied the Lipschitz equations in y to ensure a unique condition. I want you to point that out. So first, let me write down the derivative of the equation. I'm going to do separable variables. So it'll be y over 2 is equal to dt. Also take the using partial fractions here, we would get 1 is equal to y minus 2 plus by. So 1 is equal to negative 2a, but a is equal to 1/2, and also for b would be 1/2. Alright, let me just write down y squared minus 2y is equal to dt here. And then let me also rewrite this again. Let me integrate. So basically integrating both sides. And I'm going to combine the logs. So let me also denote that E2c is equal to k, and y over 2 minus 2y is equal to k e to the 2t. So we get y minus 2 is equal to y times k e to the 2t, and then y times 1 minus k e to the 2t is equal to 2. Now to find k, trying to find k, we can do y0 is equal to y0, which is equal to 1, 2 over 1 minus k. So k is equal to 1 minus 2 y0. So y of t would be equal to 2 over 1 minus 2 y0 e to the 2t, which is just equal to 2 over 2 minus y0 e to the 2t over y0. So this could be working for both. And then for any y0 is in 0, 1, the solution to the differential equations dy dt is equal to y squared minus 2y with y0 is equal to y0 is this formula. Prove that if f of a to b and g of b to c are bijections, then the compositions g times f of a to c is also a bijection. So a bijection is a function for h of x and y if it is both injective and surjective. But first I need to prove that g times f is injective. So let me write down a proof here. So let the function a to b and g, b, c be bijections. And suppose that g of x, x1 is equal to g times x of x2 for some x1, x2 is an a. Then we have g of f of x1 is equal to g of f of x2, which implies that f of x1 is equal to f of x2. And since f is injective, to show that we can also know that f of x1 is equal to f of x2 implies x1 is equal to x2. Therefore, g times x is injective. But now I need to show that g times f is also surjective as well to prove that it's a bijection. So let's take any c, and we know that since g is surjective, there exists some b such that g of b is equal to c. And since f is surjective, there also exists an a such that f of a equals b. We can see that therefore g of f of a is equal to g of f of a is equal to g of b is equal to c for every c as in c. And then we can also denote that there also exists an a such that G times f of A is equal to C. Hence, G times f is surjective. Since G and F is both injective and surjective, it is a bijection. Therefore, if f of AB and G of BC are bijections, then G of F of AC is also a bijection. Suppose that f is continuous on 0 to 3 and differentiable on 0, 1, and 2, 3. Suppose that f prime of x is less than or equal to 2 for all x in 0, 1, and f prime of x is less than or equal to 1 for all x is in 2 to 3. Prove that f of 3 minus f of 0 is less than or equal to 4. So first, let me write down a proof. So we're given that f is continuous on 0 to 3 and differentiable on 0 to 1 and 2 to 3. Now I'm going to use the mean value theorem. Let's apply the mean value theorem to f on the interval 0, 1. Then there exists a C1 between 0 and 1 such that f prime of Z1 is equal to f1 minus f0 over 1 minus 0. And given that f prime of x is less than or equal to 2 for all x between 0 and 1, and f prime of C1 is less than or equal to 2, therefore f of 1 minus f of 0 over 1 is less than or equal to 2, implying that f of 1 minus f of 0 is less than or equal to 2. And then similarly, we can also apply the mean value theorem to f on the interval 2 to 3. So similarly, applying the mean value theorem to f on the interval 2, 3. That means there also exists a C2 between 2 and 3 such that f from C2 is equal to f of 3 minus f of 2 over 3 minus 2, given that f prime of x is less than or equal to 1 for all x, which is between 2 and 3. We also see that f prime of C2 is less than or equal to 1, and therefore we could see that f of 3 minus f of 2 is less than or equal to 1, implying that f of 3 minus f of 2 is less than or equal to 1. And then let's also put f of 1 and 2. Now let's consider the interval 1 to 2. And f is continuous. And the derivative in this case is not specified. But we can know that f is continuous on the interval 0 to 3. But I don't need to account for the maximum change in f over 1 to 2. And using the given bounds, let me consider the worst case scenario where f could have a large change over 1 to 2. So let's assume that f prime of x is large. But since it's not specified, let me use f of 3 minus 0. So f of 3 minus f of 0 is equal to f of 3 minus f of 2 plus f of 2 minus f of 1 plus f of 1 minus f of 0. And putting the results together, we get f of 2 minus f of 1 can be at most large as the interval length without exceeding the constraints. So f of 3 minus f of 0 is less than or equal to 1 plus 2 is equal to 3, and f of 3 minus f of 0 is less than or equal to f of 1 minus f of 0 plus f of 3 minus f of 2, where it's less than or equal to 2 plus 1 is equal to 3. And therefore, we prove that f of 3 minus f of 0 is less than or equal to 4. Let h of a, b to r be a continuous function such that h of x is less than or equal to 0 for all x in a to b. If the integral of h over ab is 0, that is a to b of h of x dx is equal to 0, prove that h of x is equal to 0 for all x between a and b. So first, let me write down the proof. And I'm going to use this by method of contradiction. So let's assume by contradiction that h of x is not identically 0 on A to B. Which means that this implies that there exists a C between A and B where h of C is less than 0. Since we know that h is continuous on A to B, and h of C is less than 0 for some C between A and B, there must be a neighborhood around C where h of x is negative. Specifically, a delta. So that means there exists a delta which is greater than 0, such that h of x is less than 0 for all x within c minus epsilon and c plus epsilon that intersects AB, where epsilon is sufficiently small on the subinterval and where h of x is less than 0 of c, the integral between c minus epsilon and c plus epsilon of h of x dx is less than 0. And the integral is negative. Let me see that. Specifically where epsilon is chosen so that c minus epsilon and c plus epsilon is within A to B. Given that the integral of A to B of h of x dx is equal to 0, and the integral over any sub-interval where h of x is less than 0, which is negative, this leads to a contradiction. Since h of x was negative over any sub-interval, the integral over the entire integral AB would be negative. Which contradicts that f of a to b of h of x dx is equal to 0. And the assumption that h of x is not identical to 0 leads to a contradiction. So therefore, h of x must be 0 everywhere on a to b. Consider a simple population model where the growth of a population pt is governed by the logistic differential equation dp over dt is equal to rp times 1 minus p over k, where pt is the population at time t, r is the intrinsic growth rate, and k is the carrying capacity at the environment. Determine the equilibrium points at the logistic model and find the population pt as a function of time t if the initial population is p0 is equal to p. So first let me find the equilibrium points for this. So we know that dp over dt is equal to 0. So we have rp is 1 minus p over k of r. So we'll divide by rp first. Subtract 1 from both sides. And now we have pk is equal to negative 1. Then I would multiply by k right here. So negative p is equal to negative k. So p could equal k, and p is equal to 0. So now I have to find the population pt as a function in a time t if the initial population is p0 is equal to p0. So first step I would do is I would solve the differential equations. So we have dp over p times 1 minus pk is equal to r dt. I will solve the differential equations and use separation of variables for this problem. So 1 over p 1 minus pk is equal to 1 over p plus 1 over k minus p. It's like partial fractions here. pk minus p dp is equal to r dt. And all I do here is I would integrate 1 over p plus 1 over k minus p dp is equal to integral of r dt. And then from here, this would be ln of p minus ln of k minus p is equal to rt plus c. And simplifying from here, I can write ln of p k minus p is equal to rt plus c. And now I can exponentiate both sides. So p k minus p is equal to e to the rt plus c. And now we can see that p of k minus p is
is equal to C RT plus C. So let's say let C equal C1. Now I could write this as P is equal to K C1 e to the RT over 1 plus C1 e to the RT. And P of 0 would be K C1 over 1 plus C1. And using the initial conditions P0 is equal to P0 to find C1, I would write this as PT is equal to K times P0 over K minus P0 e to the RT over 1 plus P0 K minus P0 e to the RT.
Consider a particle of mass m confined in one-dimensional infinite potential well with potential energy V of x is equal to 0 for x is between 0 and L and infinity otherwise. The time-independent Schrodinger's equation for a particle of mass in this potential well is the reduced Planck constant squared over 2m times d squared of the wave function over dx squared is equal to e to the wave function, where h is the reduced Planck constant, the x is the wave function, and e is the energy of the particle. And when you're trying to solve this Schrodinger's equation for the wave function in the region x is between 0 and L, and find the corresponding energy eigenvalues even for the particle. So first let me write down the equation, which is b h squared 2m Now I can rearrange them. So let k squared is equal to 2m e h squared, then d squared over the wave function of dx squared is equal to negative k squared of the wave function. So it would be, the wave function would be a as sine x kx plus b cosine of kx. But that is the general solution. But we need to figure out the energy eigenvalues En. So let's say at x is equal to 0, the wave function is 0. Wave function of 0 is equal to b cosine 0 is equal to b is equal to 0, so b is equal to 0. So say at x is equal to L, the wavelength L, 0. So sine of KL would be 0
for non-trivial solutions where A is less than, not equal to 0. And we also see that K of L is equal to N times pi, where N is a positive integer. So K would be N pi over L when you're trying to solve for it. And we have the energy eigenvalues as h squared k squared over 2m n squared pi squared h squared over 2m l squared.
Consider the basic enzyme reaction described by the Michaelis-Menten kinematics. In the given model, an enzyme E catalyzes the conversion of a substrate S into a product P. The reaction can be described by the following system of differential equations. ds over dt is equal to negative v max s over km plus s, and dp over dt equals v max of s over km plus s, where s of t is the concentration of the substrate at time t, p of t is the concentration of the product at time t, Vmax is the maximum reaction rate, and Km is the Michaelis constant, which represents the substrate concentration at which the reaction rate is half of Vmax. Derive the expression for ds dt and dp dt based on the Michaelis-Menten equation and find the steady concentration of S and P. So first, let me write down the Michaelis-Menten equation.
So it would be ds over dt is equal to negative v mx s over km plus s.
And the Michaelis-Menten equation describes the rate of change of the substrate concentration S, and this equation is derived from the assumption that the rate of the reaction depends on the substrate concentration according to the Michaelis-Menten kinematics, and the negative sign indicates that the substrate is being consumed.
Let me also write down dB dt, which is equal to V max S over K M plus S.
And this follows directly that the product is formed at the same rate as the substrate is consumed in the enzyme catalyzed reactions. And since the product formation is proportional to the substrate concentration, S final approaches 0 as all the substrate is converted to the product.
So let me write this down. So we denote P final, which is the steady state concentration of P, is equal to the integral of 0 to infinity of V max S of t over Km plus S of t dt, where P final is the steady state concentration of P and S0 is the initial substrate concentration. And now we have P final is equal to SO minus S final. So basically that's the equilibrium all the substrates will have when being converted to the product. And S final is a low concentration or nearly 0 when the reaction is complete. And we see that also ds over dt is equal to 0, where dp dt is equal to 0. So using negative v max x over km plus s is equal to 0. So for this to hold, S must be such that v max x over kmx is equal to 0. But in particular terms, S approaches a value where the substrate is longer changing. Consider a chemical reaction network involving a single species A with the following reactions. Reaction 1 from A to 2A with rate constant K1. Reaction 2 with 2A going to A with rate constant K2. And let A and T be the number of molecules of A at time t. Determine the transitional probabilities P and A and M prime A for a time step delta t for the changes in the number of molecules of A due to these reactions using the master equation. So first off, let me write down the master equation for this. So we denote dP and A t over dt is equal to the summation of n prime a of w n prime a goes to na p na t minus w na going to na and p na t. And the mass equation describes the time evolution of the probability distribution P NAT of having Na molecules of A at time t, where W Na goes to Na is the transition from state Na to N prime A. So let me also write down dP NAT over dt, which is be K1 Na minus 1 P Na minus 1 T minus K 1 Na P of Na T plus K2 over 2 Na plus 1 of Na. We also have P Na plus 1 of T minus K2 over 2 Na. And then we have Na minus 1, the probability of Na to T. And now let's work with the reactions. So let's do reaction 1. We see that the transition is Na to Na plus 1, and the rate would be K Na. So let's do reaction 2. So the transition would be Na going to Na minus 1 for Na greater than or equal to 2. And we also have the rate, which is just K2 of Na minus 1 over 2. So let me write down the transitions from Na to Na plus 1, and that would be Kn Na. And let's also write down the transition from Na to Na plus 1, and that would just be K2 over 2 of Na minus 1 of delta T. Given the following Rivas-Shamir elements RSA public key parameters, prime number P is equal to 11 and Q is equal to 17. Public exponent E is equal to 7. Find the private exponent of E is equal to 7, data N is equal to 160. D times E mod 160, D times 7 mod 160. So first, I would need to find D, and I need to find the module inverse of 7, module 160, using the extended Euclidean algorithm to find D. So first thing I would do is I would do 7D 160. I need to find integers D and K for 7D plus 160. K is equal to 1. So let me try using the extended Euclidean algorithm. So it would be 6 is equal to 6, 1 plus 0. we see that D is equal to 23, which is the private exponent for D.
Let V be a finite dimensional vector space over a field F, and let T V to V be a linear transformation. Suppose that the kernel of T and Im of T are subspaces of V. Prove that the dimension V is equal to the dimension of the kernel T plus dimension of Im T.
First, let me write down the proof. First, let me denote let V, V2, all the way to Vk be a basis for form. Since the kernel of T is a subspace of V, the dimension of kernel T is K. So the dimension of kernel T is equal to K. Since kernel T is a subspace of V, let's extend the basis. So let's say we have V1, V2, all the way to Vk to a basis for the entire space V. And let's give this extended basis by V1, V2, all the way to Vk of U1, U2, all the way to Um. And the total number of basis vectors for V is K plus M. So the dimension of V is equal to K plus M. And now let's consider the set TU1, TU2, all the way to TUM. And since TVI is equal to 0 for all I is in T, since VI is the kernel of T, the vectors TV1, TV2, all the way to TVK are not an image of T. Thus, the image of T is spanned by the vectors TU1, TU2, all the way to TUM. And if these vectors are linearly independent, they form a basis for IMT. Therefore, the dimension of IMT is equal to M, so the dimension of V is equal to K plus M, where K is the dimension of kernel T and M is equal to the dimension of IMT. Therefore, we show that the dimension of V is equal to dimension of kernel of T plus the dimension of IM of T.
Let R be a ring and let T be an ideal of R. Prove that the set J is an ideal of R. To prove that the set J is an ideal of R, I need to show that J satisfies the two main properties of an ideal. J is a subgroup of R under addition, and J is closed under multiplication by any element of R. So first, I would prove it by closure under addition. Let me write down a proof here. And let's say let A, B, and J by definition of J, there exists an x1, x2, an I, and R1 and R2 and R such that A is equal to x1 times R1 and B is equal to x2 times R2. Let's show that A plus B is in J. So let A plus B equal x1 times R1 plus x2 times R2. Since I is an ideal, it is closed under addition, and x1 times R1 plus x2 times R2 is A plus B is equal to x1 R1 plus x2 R2. Since I is an ideal, the sum x1 R1 plus x2 R2 is an element of I times for some R. If x1 times R1 plus x2 times R2 is in J. Specifically for any combinations of elements from I and R, their sum remains in J by the property of ideals. Now let me show by the existence of additive identity. So the additive identity 0 is equal to x times 0 for all x in I, and hence 0 is in J,
and let A be in J, then A is equal to X times R for some X in I and R is in R. The additive inverse of A is negative A, and negative A is equal to negative X times R is equal to negative X times R. We know that since I is an ideal, it is closed under taking additive inverse. Thus, negative A is in J. Thus, J is closed under addition. And additive inverses, making it a subgroup of R under addition. Now I'll prove that J is closed under multiplication by any element of R using left and right multiplication closure. So let A be in J and R be in R. Let's show that R times A is in J. Since A is in J, there exists an X in I and S is in R, such that A is equal to X times S for all R in R. So we get R times A equals R times X times S is equal to R times X times S. Since I is an ideal, R times X is in I. Thus, R times A equals R times X times 7. Therefore, R times A is in J, proving closure under left multiplication. Similarly, for any R in R, A times R is equal to X times S times R is equal to X times S times R. Since I is an ideal and X is in I, X times S times R is in J. Thus, A times R is in J. Since J is closure under addition and multiplication by any element of R, it is an ideal of R. Maximize z is equal to x plus y, subject to 2x plus y is less than or equal to 4, x plus 2y is less than or equal to 4,
x is greater than or equal to 0, and y is greater than or equal to 0, using the simplex method. The first step I would do is I would convert to canonical form using the slack variables. So we have 2x plus y plus u is equal to 4, and x plus 2y plus v is equal to 4, where x is greater than or equal to 0, y is greater than or equal to 0, u is greater than or equal to 0, and v is greater than or equal to 0. So z is equal to x plus y, and negative x minus y plus v is equal to 0. And now let me create a tableau or a table. So we have x, y, u, v, z here. We have u, v being down here. We have 2, 1, 1, 0, 0, 1, 2, 0, 1, 0. We have a 4, 4 down here, and a negative 1, 0, 0, 1, 0. And basically I would look at the most negative entry row, and I'll also have to decide on the pivot column. And to decide the pivot row, I would do 4 over 2 is equal to 2 for the first row, and 4 over 1 is equal to 4 for the second row. So let me write this down here. We have x, y, u, v, z. We have, we have u and v. So this would be 1, 1 half, 1 half, 0, 0, 2. This would be 1, 2, 0, 1, 0, 4. Then we have negative 1, 0, 0, 1, 0. And now up here, I could do x, y, u, v, z. And I would do x and v. So I have 1 half, 1 half, half, 0, 0, 0, 3 halves, negative 1 half, 1, 0. And then this, 1. So we have 2, 2, 2. And all we do is I would do R2 minus R1 to get R2, and R3 plus R1 to get R3. And also down here I would do R, half R by R1. So for that one I wanted to make the pivot entry 1 by dividing by 2. Let's do the same for this one. For x and y here, be 1, 0, 2 thirds, 1 third, 0, 0, 1, negative 1 third, 2 thirds, 0. So it'd be 4 thirds, 4 thirds, 8 thirds. We have 0, 0, 1 third, 1 third, 1. Now all I just did was I did R1 minus R2 to R1, and then R squared plus R2, R2 to R3. And now we have the optimal solution, which is x is equal to 4 thirds, y is equal to 4 thirds. So this is the optimal solution. And the optimal value is c is equal to 8 over 3. There are 3 doctors, D1, D2, D3, and 3 hospitals, H1, H2, H3. Each doctor and hospital has ranked the members of the opposite group according to the precedence for working together. The goal is to find a stable matching where no doctor-hospital pair would prefer to be matched with each other over their current assignments. So we have the doctor's preference, where D1 is H2, is greater than h, D3 is greater than h1, D2, h1 is greater than h2 is greater than h3, and D3, h3 is greater than h1 and greater than h2. And we have the hospital reference where h1 and D2 is greater than D3 is greater than D1. H2, we have D1 is greater than D2 is greater than D3, and H3 where D3 is greater than D1 is greater than D2. Use the Gale-Shapley deferred acceptance algorithm to find the stable matching between doctors and hospitals. So first off, let me write down the initial proposals. So for round 1, this would be the initial proposals. So D1 proposes to H2, and D2 proposes to H1, and D3 proposes to H3. And basically I solved this where the doctors proposed to the hospitals. And now let's see the matchings after round 1. So you have D1 to H2, D2 to H1, we have D3 to H3. Since every doctor is matched with their first choice, and no one is rejected. So therefore the process stops. Now we have the final matching. D1 is matched with H2. D2 is matched with H1, and D3 is matched with H3. Find the greatest common divisor, GCD, of 252 and 198 using the Euclidean algorithm. First off, let me do 252 divided by 198 is 1 remainder of 54. And 198 times 1 plus 54 is 252. Let me also do 198 divided by 54. That is just 3 remainder of 36. So 54 times 3 plus 36 is equal to 198. Let me do 54 divided by 36. That'll be 1 remainder of 18. So 36 times 1 plus 18 is equal to 54. And 36 divided by 18 is equal to 2, remainder of 0. So 18 times 2 plus 0 is equal to 36. And using the Euclidean algorithm to apply the division algorithm until the remainder is 0. And since the remainder is 0, the GCD is the last non-zero remainder, which is 18. So therefore, the answer is 18, the GCD of 252 and 198. Consider the sequence of numbers x0, x1, x2, x3, given by x0 is equal to 1, x1 is equal to 2, x2 is equal to 3, and x3 is equal to 4. Find the discrete Fourier transformation, or the DFT, of the sequence. So first, let me write down the sequence. So it'd be xk is basically the summation of n minus 1, n is equal to 0, of xn times e to the negative I 2 pi k over n for k is equal to 0, 1, 2, 3,
where e to the negative I 2 pi over n is the primitive nth root of unity. So let me figure out x0. So it'll be x0 is equal to negative I 2 pi 0 times 0 over 4 plus x1 times e to the negative I 2 pi 0 times 1 over 4 plus x2 times e to the negative I 2 pi 0 times 2 over 4 plus x3 times e to the negative I 2 pi times 0 times 3 over 4. And we can see that x0 is equal to 1 plus 2 plus 3 plus 4 is equal to 10. Let me do x1 next. And I can just simplify more from here. So I got x0 is equal to 10 and x1 is equal to negative 2 plus 2i so far. Now let me do x2. We do some simplification here. So x2 would be 1 minus 2 plus 3 times 1 minus 4 is negative 2. There we go. We have x2 is equal to negative 2. And finally, let me figure out what x3 is.
So I figured out what x3 is, and it's -2 minus 2i.
So now let me write down the coefficients for each one. So the discrete Fourier transform DFT of the sequence 1, 2, 3, 4 are these coefficients represent the frequency components of the original sequence.
So x0 is equal to 10, x1 is equal to -2 plus 2i, x2 is equal to -2, and x3 is equal to -2 minus 2i. Prove that the set of all finite subsets of natural numbers n is countable.
Let me write out the proof. So let's consider each finite subset of n as a sequence of elements from n with a finite length. Each finite subset can be represented as a string of zeros and ones, where the ith position is 1. If the number I is in the subset and 0 otherwise. So let's take an example, the subset one, 3, and 4, which can be represented as 1, 0, 1, 1, etc., which is the first which is the first, third, and fourth positions. Since each finite subset has a corresponding finite binary string, and the set of all finite subsets of n is countable, the set of all finite subsets of n is countable. Therefore, the set of all finite subsets of n is countable.
Given the following set of data points, x is 1, 2, 4, and f of x is 2, 3, and 1, find the Lagrange interpolating polynomial p of x that passes through these points and use the interpolating polynomial px to approximate p3.
So the first step I would do is I would write the formula for the Lagrange interpolating polynomial for p of x. So p of x is equal to the summation of n of I is equal to f of x times li of Lx. And let me also write down the Lagrange basis polynomial for Li of x. And that would be xi minus xj. And also let me write down also the points. So we have x1 f of x1 is equal to 1, 2. We have x2 f of x2 is equal to 2/3. We also have x3 f of x3 is equal to 4, 1. So let me write down L1 of x, which is just equal to x minus 2 times x minus 4. 1 minus 2 times 1 minus 4. And then like simplifying from here, get -1 times -3, which is just x minus 2 times x minus 4 over 3. Now let me do L2 of x. That would be x minus 1 times x minus 4. 2 minus 1 times 2 minus 4 is equal to x minus 1 times x minus 4 over 1 times -2. This is just negative x minus 1 times x minus 4 over 2. Now let me do L3 of x. And that is x minus 1 times x minus 2 over 4 minus 1 times 4 minus 2. And this is equal to x minus 1 times x minus 2 over 3 times 2. We have x minus 1 times x minus 2. That is 6. And now let me write down the Lagrange interpolating polynomial. So it would be p of x is equal to 2 L1x plus 3 L2x plus L3 of x. So this is the Lagrange interpolating polynomial. And now let me also plug in the values of L1 of x. So I'm going to do this. P of x is equal to 2 times, on the numerator, you have x minus 2 times x minus 4 over 3. We have a plus 3 negative x minus 1 x minus 4 over 2 plus, let's do x minus 1 times x minus 2 over 6. Now let me simplify from here. So let me plug in 3 into the interpolating polynomial p of x. So it would be let me also do simplify from here. So I have 8/3, and then this is 2.67. So I could write P3 is equal to 8/3, or roughly 2.67.
Consider the complex function f of z is equal to z minus I over z plus I. Show that f of z maps the upper half plane, that is, the image of z is greater than 0. Conformally onto the unit disk, the absolute value of w is less than 1 in the complex plane. And to determine the image on the f of z of the imagery axis, the real parts of z is equal to 0.
So first, let me show. So let z is equal to x plus I, where x, y is an r, and y is greater than 0. So let me rewrite the function. F of z is equal to z minus I over z plus I. We can expand this to x plus I, y minus 1. And then this would, the denominator would be I plus x plus I, y plus 1. F of z would be x plus I, y minus 1. Basically, I'm multiplying the numerator and denominator by the complex conjugate of the denominator. So this would be x minus I, y plus 1. This on the denominator would be x plus I, y plus 1. And we have x minus I, y plus 1. And now let me expand this again. It'd be x squared plus x, y plus 1, I minus x. And we have y minus 1, I plus y minus 1 times y plus 1. And we have x squared plus y plus 1 squared. And let me write this up here. Simplifying from here, we get x squared plus y squared minus 1 plus 2yi over x squared plus y plus 1 squared. Now let me find its magnitude. So f of z squared is equal to x squared plus y squared minus 1 squared plus 4y squared over x squared plus y squared plus 1 plus 2y squared.
And since the absolute value of f of z is less than 1 for the upper half plane, where y is greater than 0, I need to show that the image lies with the unit disk. And since
Y is greater than 0, it's less than 1, implying that f of z, or the absolute value of f of z, is less than 1.
And therefore, the function maps the upper half plane conformally onto the unit disk. And now for the imagery axis, for x equals 0, so z is equal to x, z is equal to iy, where I is a real number. So let me write this down. So f of iy is iy minus I over iy plus I is equal to I, take out the I. The i's cancel, and now we have y minus 1 over y plus 1. Let me write this as w is equal to y minus 1 and y plus 1. And this shows that the image of the imagery axis under f of z is the real number, as y goes from negative infinity to infinity, and w goes from, and we see that w goes from to negative absolute value w. And now this would be, let me also write that down. This would be the image of the imagery axis is the interval on the real axis of the w plane. Suppose g of n is a sequence of functions g of n e to r, where e is a subset of r, and suppose that each function g of n is uniformly continuous on e, and the sequence g of n converges uniformly to a function g of e to r. Prove that g is uniformly continuous on e. So first, I'm going to write down by the uniform convergence. So write the proof. So by the uniform convergence for all epsilon greater than 0, there exists a natural number n such that the distance between g of n of x minus g of x is less than epsilon over 3, where n is greater than equal to n for all x in E. We know that since g of n is uniformly continuous, there exists a delta greater than 0 such that the distance between x and minus y is less than epsilon, which implies that the distance between g n of x times g n of y is less than epsilon over 3 for all x, y in E. Let's say for a fixed x in y such that the distance between x minus y is less than delta. And let me show you that the distance between g of x minus g of y is less than epsilon. So let's show that the distance between g of x and g of y is less than epsilon. First, let me do g of x minus g of y is less than or equal to g of x minus g n of x plus g n of x minus g n of y plus g n of y minus g of y. Now the distance between g of x minus g of y is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3, which is just 3 epsilon over 3, and these cancel, and we have epsilon. So therefore, for x minus y is less than epsilon delta, the distance between g of x minus g of y is less than epsilon, proving that g is uniformly continuous
on E.
Let a of n be a sequence of real numbers, and consider the power series f of x is equal to the summation of a n of x of n. Assume that the power series converges for some x0 in R, that is, the summation of a n x0 to n converges. Prove the power series converges absolutely for all x such that the absolute value of x is less than the absolute value of x0. So I'm going to prove by the assumption of the series. So let me write down a proof. By assumption, the series
converges, implying
that the radius
of convergence R of the power series is at least the absolute value of x is 0. That is, the absolute value of x is less than R for convergence of the summation of a of n x of 1. Let me also point out that the radius of convergence let me call it R, and let me give you the definition of what the radius of conversion is. It's defined as denote 1 over R is equal to the limit as n approaches infinity of the supremum of a n 1 over n. Since the series converges at x0, we can also see that the absolute value of x0 is less than R. Therefore, for any x such that the absolute value of x is less than the absolute value of x0, we can conclude that the absolute value of x is less than R. And let me also consider another sequence, that is a series with an absolute value. So let me consider the series basically the same series, but now with an absolute value. A of n x n with the absolute value. And basically I need to prove that the series converges absolutely. And given that since the absolute value of x is less than absolute value of x0, there exists an epsilon such that the absolute value of x is equal to the absolute value of x0 minus epsilon, since the power series converges at x0 for absolute value of x is less than the absolute value of x0. And the series converges absolutely
by the properties of power series. So let me show you how it's converged. So let me take the absolute value of an x of n is less than or equal to a n x0 n over the absolute value of x and x0 raised to the n power. And we also see that since the absolute value of x over absolute value of x0 raised to the n is less than 1, we can see that the series converges. Since the geometric series has a ratio less than 1, and therefore the power series converges absolutely. Such that x is less than x0 for all x. Find the Laplace transform of the function f of t defined by f of t is equal to t squared e to the 3t of sine of 2t. But first off, let me write down the formula of the Laplace transform of e to the at f of t. So we have L of f of t is equal to f of s. We also have L e to the at f of t is equal to f s minus a. And what's given is that we know that a is equal to 3. So let me write it down. L e to the 3t t squared times sine of 2t is equal to t squared sine of 2t, where s goes to s minus 3. And let me write down the Laplace transform of sine of bt. Sine of bt would be b over s squared plus b squared. And now sine of 2t is b is equal to 2, and we see that sine of 2t, based on plugging in, I'll just write down 2 is over s squared plus 4. And now let's find the Laplace transform of t squared sine of 2t. So we have L t squared sine of 2t, which is just d squared over the derivative s squared of 2 s squared plus 4. Now let me take its derivative, working it out.
Take a derivative again. So this would be negative 4 s squared plus 4 minus 16 s squared over s squared plus 4 to the third is equal to negative 4 s squared plus 16 minus 16 s squared over s squared plus 4 to the third. And now we have, simplifying from here, we have negative 12 s squared plus 16 over s squared plus 4 to the third. And this is 12s squared minus 16 of s squared plus 4 to the third. Let me write it up here. So we have 12s squared minus 16 over s squared plus 4 to the third. Now we'll like to apply the shift theorem for e to the 3t. So let me write that over here. Just basically doing s minus 3 squared. So we get the Laplace transform is equal to 12 times s minus 3 squared minus 16 over s minus 3 squared plus 4 to the third. And basically this is the Laplace transform of f of t, t squared e to the 3t sine of 2t. Consider the following boundary value problem for the heat equation ut is equal to uxx with boundary conditions u of 0x is equal to 0 for x is between 0 and L, where ut t0 is equal to 0 for t is greater than or equal to 0, ut of tl equals 0 for t is. Consider the following boundary value problem for the heat equation ut is equal to uxx with boundary conditions u0x is equal to 0 for x is between 0 and L, ut t0 is equal to 0 for t is greater than or equal to 0, ut tl is equal to 0 for t is greater than or equal to 0, u of x0 is equal to f of x for x is between 0 and L, where f of x is a given function and utx is the temperature distribution. Solve the partial differential equations using the Fourier series method. So first I want to assume the solution of the form. So let me write down the form. So be utx is equal to tt times xx. Now I would like to plug in into the heat equation. So it'll be t prime t of xx is equal to tt x double prime x. And now I would like to separate the variables by dividing through ttxx. And now let me write this. And now like we can see here that it is an ordinary differential equation. And this equation is a second linear order differential equations with boundary conditions ut t0 is equal to 0 and ut tl is equal to 0. And it basically translates to x prime 0 is equal to 0 and x prime l is equal to 0. So let me write down lambda is equal to n pi over L squared for n is equal to 0, 1, 2, all the way up. And then we have xn of x is equal to cosine of n times pi x over L. And now we can I can solve for t for each n, which is a time dependent. And now let me write down the initial condition, which is u of x is equal to f of x, which is up here. So f of x is equal to the summation of b of n cosine of n pi x over L. And now to determine b of n, I'm going to use the orthogonality of the cosine functions. So let me write down b of n is equal to 2 over L, 0 to L, of f of x cosine of n pi over x divided by L. And let me put that dx there. And now to show that the eigenvalues are orthogonal, let me take the integral of 0 to L cosine of n pi x over L times cosine of n pi x over L dx. And this could be written as cosine of n pi x over L cosine of n pi x over L is basically 1/2 cosine of n plus n pi x over L plus cosine of m minus n pi x over L. And now let me take the integral of cosine of n pi x over L times cosine of n pi x over L dx. And this is just 1/2 L over 2 delta of mn plus L over 2 delta of n minus m 0. And delta mn is the connector delta function, which is m is equal to n and 0 otherwise. So basically, we get cosine of m pi x over L cosine of n pi x over L dx is equal to L over 2 delta mn. Which shows that the eigenfunctions cosine of n pi x L are orthogonal with respect to the given boundary conditions. Let G be a graph with n vertices where n is greater than or equal to 4. Prove that either G or its complement GC contains at least 2 vertices or degree at least 1. Let me write down the proof here. And I'm going to show this by contradiction. Let's assume by contradiction that both G and GC have all vertices with degree 0. If all vertices in G have degree 0, then G is an empty graph with no edges. And if G is an empty graph, with no edges, and if G is an empty graph, then GC is a complete graph on n vertices. So the first case I have to prove is that all vertices in G have degree 0. In GC, each vertex will have a degree of n minus 1. Since all possible edges are present for n is greater than or equal to 4, n minus 1 is greater than or equal to 3. So each vertex in GC has degree at least 3. Now I have to prove that GC has a degree 0. So in GC, if every vertex has degree of 0, then G must be a complete graph. Meaning that all possible edges are present. So let me write that down. And if G is a complete graph, then GC is an empty graph. Therefore, G is a complete graph. And all vertices in G have degree n minus 1. And in both cases, I have contradictions with the assumption that both G and GC have all vertices with degree 0, showing at least one of the graphs, G or GC, must have vertices with degree at least 1. If G has all vertices with degree of 0, then the complement of GC is a complete graph with n is greater than or equal to 4. So GC has at least 2 vertices with degree n minus 1 is greater than or equal to 3. If GC has all vertices with degree of 0, then G is a complete graph with n greater than or equal to 4. So G has at least 2 vertices with degree of n minus 1 is greater than or equal to 3. Therefore, either G or the complement of G contains at least 2 vertices with degree of at least 1. Let alpha IR3 be a smooth curve where IR is an open interval. Suppose alpha t is a regular curve. That is, alpha prime t is not equal to 0 for all t in I. Define the vector field. Show that Vt is orthogonal to both alpha t and alpha prime t. So let me write down the proof. So let's consider the dot product of V of t with alpha t and V t times alpha t is equal to alpha t times alpha prime t times alpha t. And we get using the property of scalar triple product which is equal to 0, since the cross product alpha t times alpha prime t is orthogonal to both alpha t and alpha prime t, and the dot product of a vector with itself or another vector that is orthogonal to it is 0. So Vt times alpha t is equal to 0. And now let's consider the dot product of Vt with alpha prime t and Vt times alpha prime t is equal to alpha t times alpha prime t is equal to alpha t times alpha prime t times alpha prime t. Similarly, using the property of the scalar triple product, alpha t times alpha prime t times alpha prime t is equal to 0. The vector at times alpha prime t is orthogonal to alpha prime t, since it is perpendicular. Both alpha t and alpha prime t, thus Vt times alpha prime t is equal to 0. Hence, the vector field Vt is equal to alpha t times alpha prime t is orthogonal to both alpha t and alpha prime t for all t and I.
Show that the angle sum of any pentagon is 3 pi. So first off, I would like to draw a visualization of a pentagon. Let's denote this as A, B, C, D, and E. And first, I want to show and write down a proof. So first, let A, B, C, D, E be a pentagon. And we know that triangle ABC, triangle ACD, and triangle ADE. So basically, I'll draw a line from here, here. Now we have triangle ABC, ACD, and ADE. And we could see that we have a diagonal that I drew, AC and AD, from one vertex to non-adjacent vertices. And now it divides the pentagon into 3 triangles. And we also know that the sum of the interior of each triangle is pi, or 180 degrees. And the sum of the angle for each triangle let's say in ABC is pi. Triangle in ACD is also pi. And triangle in ADE is also pi. And the interior angles of the pentagon are the sums of the angle in the three triangles minus the angles around point A. So let me write down the total sum. Would just be pi plus pi plus pi is just 3 pi. So hence, we see that the angle sum of any pentagon is 3 pi. Let q be a prime number and let x be an integer such that x is not divisible by q. Suppose the smallest integer d satisfies xd congruence 1 mod q. Prove that d is a divisor of q minus 1. Let me write down the proof here. Since we know that q is a prime number, and x is not divisible by q, by Fermat's theorem, little theorem, x of q minus 1 is congruent to 1 mod q. And this means that the order of x modulo q must divide q minus 1. And now let me give the definition of the order q. So the order d of x modulo q is defined as the smallest positive integer such that x to the d congruence 1 mod q. And now I'm going to show you the relation between d and q minus 1. So since xq minus 1 is congruent to 1 mod q by Fermat's little theorem, and xd is congruent to 1 mod q by the definition of the order, it must be that q minus 1 is a multiple of d, and q minus 1 is equal to kd for some integer k, implying that d divides q minus 1. And therefore we see that the smallest positive smallest positive integer d such that xd congruent to 1 mod q is a divisor of q minus 1. Let xd be a metric space and let f of xx be a contraction mapping, meaning that there exists a constant c between 0 and 1, such that for all x and y in x, and the diameter of f of x of y is less than or equal to c times d of xy. Suppose that x is complete. Prove that f has a unique fixed point in x. That is, show that there exists a fixed point in x such that f of the fixed point is equal to the fixed point x. So first off, let me start off by writing a proof. So let's start with an arbitrary point. Let's call it x0 is an x. And let's take a sequence xn defined by, say, xn plus 1 is equal to f of xn. For n is equal to 0, 1, 2, etc. And basically I want to show that xn is a Cauchy sequence. So for m greater than n, we take that dn plus 1 of xn is equal to d of f of xn times f of n minus 1 is less than or equal to c times d x of n minus 1 and dxn plus 2 over xn plus 1 is equal to d of f xn plus 1 over f of xn is less than cd of x of n plus 1 x of n. And then by continuing this process, I can apply the contraction. Let me write that also down. By continuing this process, I can apply the contraction repeatedly to get d of xn plus k of x of n plus k minus 1, which is less than or equal to ck times d for m is greater than or n, meaning that the distance between x of m and x of n is bounded by, so we see that the distance
between x of m and xn is less than or equal to d of n plus 1 x of n plus d of x n plus 2 of x n plus 1 plus all the way to, so call it dx of n and x of n minus 1. And also the distance of d of x of m, x of n, is less than d of x0 of cn plus cn plus 1 plus all the way to cn minus 1. And d xn is less than d of 1 x0 times c of n times 1 minus c m minus n over 1 minus c.
And we see that the sum of the series is a geometric series as n approaches infinity. And the right hand side tends to 0 since c is between 0 and 1, meaning that xn is a Cauchy sequence. And now I'm going to prove it by the convergence of sequence. So let me write that down here. So we know that since x is complete, the Cauchy sequence converges to some fixed point. So we call that and now I need to show that the fixed point is in f. That is, f of the fixed point is equal to the fixed point x. So xn approaches the fixed point as n approaches infinity. We know that since xn approaches the fixed point, f of xn is equal to xn plus 1, which approaches f of x, the fixed point f of x, and as n approaches infinity. But x of n plus 1 approaches fixed point x. So by uniqueness of limits, f of x is equal to the fixed point of x. And using the uniqueness of the fixed point, suppose there are two fixed points. Let's denote that as x and y, such that f of x equal to the fixed point x and f of y is equal to the fixed point y. Then d of the fixed points x and y here is equal to the distance of f of x, f of y. Since we know that c is between 0 and 1, the inequality d
of x and y at the fixed point is less than or equal to, let's call it c times d x y, implying that d of x and y is equal to 0. Therefore, f of x, the fixed point x, is equal to the fixed point x. And therefore, I proved that the fixed point is unique. And the contradiction mapping F has a unique fixed point.
Let x and y be topological spaces, and let f of xy be a continuous map. Consider the following conditions. If x and y are both simply connected spaces, that is, they have trivial homology groups, h of 1x is equal to 0 and h of 1y is equal to 0, the map F induces a map on the first homology groups. We have F map times h1x goes to h1y. Prove that if h of 1x is equal to 0 and h of 1y is equal to 0, then the induced map F is the 0 map. That is, F to h is equal to 0 for all h inside h of 1x. So let me write down the proof. So first off, let me say that
Let h be an h1,
and since we know that
h1x is equal to 0, h is trivial, meaning that h represents the 0 class in h1x.
the map F induces
F,
and by definition of the induced map, it maps h
to
f of h
in h1y. Since
h
is trivial in h1x, of h1 must be trivial in
h1y. Since h1y
is equal to 0,
every element
in h1y is also trivial.
Therefore, the mapping
H
must be
the 0 element in
h1y. Let R be a cumulative ring with unity, and let I and J be ideals of R. Prove that the intersection I, J is an ideal of R.
So first off, I need to prove that the intersection of I and J is an ideal of R. And I need to show that the intersection of I, J is non-empty.
So first, let me write out the proof. First off, I'm going to say that since both
I and j are ideals of R, and both contain the zero element, which is 0 in R, it follows that 0 is in J, well, it's in I, intersection J. Thus, the intersection of I, J is non-empty. And now I have to show that the intersection of ij is closed under addition. So let A, B be in the intersection of I and j, then A is in I and A is in j. Similarly, B is in I and B is in j. Since I and j are ideals, they are closed under addition, which is A plus B in I. Since I is an ideal and A plus B is in J, since J is an ideal, therefore A plus B is in the intersection of I and J, and hence the intersection of I and J is closed under addition. Now that I proved that the intersection of I and j is closed under addition, I also need to show that the intersection of I and j is closed under multiplication by elements in K. I'm going to show that. So let R be in R and A be in the intersection of I and j. Then A is in I and A is in j. Since I and j are ideals, they are closed under multiplication by any element of R. So R times A is an I. Since I is an ideal and R times A is in J, since J is an ideal, therefore R times A is in the intersection of I and j. And hence, the intersection of I and j is closed under multiplication. elements in of R. Thus, the intersection of I and J satisfies the condition of being an ideal in R.
Let P of x equal x to the fourth minus 2 be a polynomial over the field Q. Prove that the Gauss group gal K over Q is isomorphic to D4, the dihedral group of order 8.
So let me write down the proof here. So we know that the Gauss group can rotate the roots corresponding to the Cyrillic subgroup of D4 generated by 90 degrees and 270 degrees rotations. It can reflect the roots corresponding to the reflections in D4, which swap pairs of roots, and thus the automorphisms of K that maps corresponds to the elements of D4. Therefore, we could see that the Gauss of K over Q is isomorphic to D4.
Consider the following linear program minimize CTX subject to AX is greater than or equal to B, where A is M times N matrix, B is a M-dimensional vector, and C is a N-dimensional vector. Prove that if there is no feasible solution, then there exists a vector y is greater than or equal to 0, such that ATY is less than or equal to Z, and BTY is greater than 0. So I'm going to use Farca's limit to prove this first. So let me write down the proof.
So using Farca's lemma, and I want to point that out, for any matrix, so we have A, which is an R M times N, and vector B is an R of N. Exactly one of the following two systems has a solution. It could be AX is greater than or equal to B with x is greater than or equal to 0 has a solution, and we could also say that aty is less than or equal to 0 with bty is greater than 0, which also has a solution. By assumption, there is no feasible solution to the linear programming we have ax is greater than or equal to b with x is greater than or equal to 0, implying that the system ax is greater than or equal to b has no solution. If the primal system ax is greater than or equal to b has no solution, then the dual system aty is less than or equal to 0 and bty is also greater than 0 must have a solution for some vector. I might call this y is in R of n. Hence, the non-existence of a feasible solution to ax is greater than or equal to b implies the existence of a vector y satisfying aty is less than or equal to z and bty is greater than 0.
A certain type of puzzle involves arranging tiles in a grid. Specifically, you have a grid of n times 2 cells and want to fill the grid with 2 types of tiles. Horizontal tiles, where each tile covers exactly 2 adjacent cells in a single row, and vertical tiles, where each tile covers exactly 2 adjacent cells in a single column. Let A of n represent the number of ways to completely fill a n times 2 grid. The number of ways to completely fill a n times 2 grid with these tiles. Find a recurrence relation for A of n and solve it to determine A of n for small values of n. So first, I want to write down the base case. So we start with a base case of n is equal to 1. And basically, there is only one way to fill a 1 times 2 grid, which is by placing one horizontal tile. So A of n is equal to 1. So I'm going to write down the recursive case, where n is greater than or equal to 2. So for the first case, I can place a vertical tile in the first column, leaving a n minus 1 times 2 grid to fill. And the number of ways to fill this remaining grid is a n minus 1. And then I can place 2 horizontal tiles in the first rows, leaving n minus 2 times 2 grid to fill. The number of ways to fill this remaining grid is a n minus 2. So let me write down the recursion relation
So if an is equal to an minus 1 plus an minus 2. And up here, let me solve the recurrence relations using the recurrence relations and the base cases. So a1 is equal to 1, a2 is equal to 2, since I can either place 2 vertical tiles or 2 horizontal tiles. And now n is equal to 3, so a3 is equal to a2 plus a1, and a3 is equal to 2 plus 1 is equal to 3. Let's do n4. So basically that would be 3 plus 2 is 5. And let me do n is equal to 5. So it'll be a5 is equal to a4 plus a3. So a5 is equal to a5 plus 3 is 8. And now we have n is equal to 1, 2, 3, 4, 5, and 1, 2, 3, 5, and 8.
Consider an infinite tree T where every node has a finite number of successors. Formally, let T be a rooted tree such that for every node V is in T, the set of nodes W, VW is in E, has a finite cardinality. The tree T is infinite, which has infinitely many nodes. Prove that T contains an infinite path. First, let me write down a proof. Now let's consider a infinite tree T defined as VE, where V represents the set of nodes and E is a subset of V times V, which represents the edges. The tree T is rooted and infinite, meaning that V is a infinite set. For each node let suck V is equal to, the successors be equal to W, VW is an E, denote the set of nodes directly connected to V. And using Koenig's lemma, if T is a infinite tree where each node V has a finite number of successors, then
T must contain an infinite path. And this lemma applies to trees where each node V has a finite branching factor, meaning that the success of V is a finite for every V. Since each node in T has a finite number of successors, and the tree is infinite, so we know that Koenig's lemma guarantees the existence of an infinite path. And now let me construct it. So let's start with an infinite path at the root node V0 of T. And now let me choose a successor. Let's call it Vn plus 1, such that Vn plus 1 is an E. Since we know that T is infinite, and every node has finitely many successors, this process of moving from one node has to its successor will yield an infinite sequence. So let's say Vn, n is an n of distinct nodes. Hence, using Koenig's lemma, T contains an infinite path.
The average number of customer complaints per week at a certain store is 3. Find the probability that in a given week there are exactly 2 complaints, 4 or more complaints. So this is an example of using the Poisson distribution. So let me write down
the Poisson distribution formula. Where lambda is the average rate of events occurring in the interval, and k is the actual number of events. So first I'm trying to figure out
what is the probability that in a given week there are exactly 2 complaints. So I would denote P x is equal to 2, and then just plug in the numbers. So I should get 0.2241. So the probability that x is equal to 2 is 0.2241. And now I need to figure out what is the probability that in a given week there are 4 or more complaints. And to find the probability of having 4 or more complaints, I would first find the probability of having fewer than 4 complaints. That is 1, 0, 1, 2, 3 complaints. So I would denote the probability that x is greater than or equal to 4. It's really just 1 minus the probability that x is less than 4. But let me write that down. It's really just probably x equal to 0 plus probably x is equal to 1 plus the probability that x is equal to 2 plus the probability that x is equal to 3. And let me, using the Poisson distribution, let me find out. Just plug in the numbers here. Let me do more simplification here. That would be 1 minus 0.0498 plus 0.494 plus 0.2241 plus 0.2231. Let's do some more simplification here. It'll be 1 minus 0.6464, which is just 0.3536. The probability that x is greater than or equal to 4 is 0.3536. So the probability that in a given week that there are exactly 2 complaints is 0.2241 or 22.41%. And the probability that in a given week there are 4 or more complaints is 35.3536, or in other words, 35.36%. Consider a simple system where a machine operates in 2 states, working and broken. The machine can transition between these states. If the machine is working, it can remain in the working state with probability p, or it can break down and move to the broken state with probability 1 minus p. If the machine is broken, it can be repaired and returned to the working state with probability r, or it can stay broken with probability 1 minus r. Find the steady state probabilities of the Markov chain and determine the expected number of steps for the machine to return to their working state, starting from the broken state. So before I find the steady probabilities of the Markov chain, I would need to write the transitional probability matrix. So first off, let me denote as P is equal to P1 minus P, R1 minus P. And now I'm going to write down the steady state probability vector. Let's denote that as pi. So pi W is for broken, for work, and pi B is for broken. Note pi P is equal to pi. So now I have pi W, pi B is P1 minus P, R1 minus R is equal to pi W, pi B. Let me set this up.
would be pi w 1 minus p plus pi b 1 minus r is equal to pi b pi w plus pi b is equal to 1. And now let me set this up again and let me try to solve for b here. We have r eb is equal to 1, therefore eb is equal to 1 over r, which is the expected number of steps to return to working from broken state.
Suppose x1, x2, all the way to xn is a random sample from a population with the probability density function f of x data is equal to 3x squared over data cubed for x's between 0 and data and 0 elsewhere. Find the estimator for data using the method of moments.
So first, let me write down e to the x is equal to the integral of 0 to data of x times f x data dx. So the expected would be 0 to data x times 3x squared over data cubed dx. So it would be 3 over data cubed 0 to data x cubed dx. Now let me work with the x cubed integral, so that's just x4 to the 4th. So that would be zero would just be 0, 4 over 4, and then subtracting these, we get pi over 4 pi data over to the 4th over 4. Now I have to also multiply this by 3 over data cubed because I have it on the outside. And from here, this would give us 3 data over 4. Now let me find the variance of this. So basically I found the expectation first. So that would be e to the x squared minus e of x squared. So basically I found e to the x by just squaring it. But now I have to find e to the x squared next. So this would be 3 data squared over 5. And now let me find the variance of this, plugging in. So we have 3 data squared over 5 minus 3 data over 4 squared. And that would give us 3 data squared over 5 minus minus 9 data squared over 16. And simplifying from more here, we get, I can write this as 48 data squared minus 45 data squared over 80. And just 3 data squared over 80. And now let me write down the sample mean. B1 over n. So I is equal to 1 of xi. So this is the sample mean of x bar. So x bar is equal to 3 data over 4. So we have to, and then the method of moment estimator is just basically I have to find, so in terms of data hat, it's just 4 x bar over 3. So the method of moments estimator for data is 4x bar over 3. Suppose you are considering a European call option and a non-divide and paying stock. The current stock price S0 is $50, the strike price K is $52, and the option expires in 6 months. The annual risk-free interest rate R is 5%, and the stock's volatility data is 20% per year. Use the Black-Scholes formula to determine the price of the call option. So let me write down the formula for the Black-Scholes formula. It's C is equal to S0 and D1 minus K e to the negative RT times ND2. And we're also given that S0 is equal to 50, which is the current stock price, K is equal to 52, which is the strike price, T is equal to 0.5, which is the time monthly in years, or the time to maturity in years, and R is equal to 0.05, which is the annual risk-free interest rate, and also that data is equal to 0.2, which is the volatility. So let me write in terms of D1. R plus data 2 squared over 2 over T over data square root of T. We also have D2 is equal to D1 minus data dt. So let me plug in. So all I know, 50 over 52 is just 0.9615 is equal to negative 0.0398. So it'll be 0.398 plus 0.05 plus 0.02 times 0.5, and that would be over 0.2 times 0.7071. And I'm doing some simplification here. Over 0.1414, which is just negative 0.2461 for D1. And now let me find D2. So it's just D1 minus 0.2 times 7 0.7071. So D2 is equal to negative 0.2461, which we have below there. And then that would be minus 0.1414, which is just negative 38.75. And now I need to find ND1 and ND2, or capital ND1 and capital ND2, which are cumulative distribution functions, or the CDF of the standard normal distribution, and using the D1 and D2 normal distribution tables. So let me denote ND1 is negative 0.42461 is 0.4021, and we have ND2 is negative 0.3875 is 34.93. And now I need to find the call option price C. So C is equal to 50 times 0.4021 minus 52 times E to the negative 0.05 times 05 times 0.3493. Let me do some simplification here. That'll be 0.04401 minus 52 times 0.9753 over 3493. And I get an approximation that C would be, we do 20.105 minus 17.704, which is roughly $2.40. So the price of the European call option is approximately $2.40. Consider a life insurance policy with the following characteristics. Policy type: whole life insurance. Sum assured is $200,000. Annual premium is $3,000. Interest rate is 5% per annum. Mortality rate, and let's assume that the mortality rates are given by Q of X, where Q of X is the probability that a person age X will die within 1 year. So let's just say that Q40 is equal to 0.01. That is the probability of dying between age 40 and 41, and Q41 is equal to 0.002. Basically, that's the probability of dying between age 41 and 42. Mortality rates increase by 0.001 per year. So I need to find the net single premium NSP for the policy if the policyholder is 40 years old. The NSP is the present value of the expected death benefit under the policy, discounted at the interest rate. So first, let me write down the NSP, or the net single premium. Note, NSP is equal to the summation T is equal to 0 to infinity. We have the benefit times the probability of death at T times 1 over 1 plus T to the T. Now the probability of death at T is just T minus 1, K is equal to 0, of 1 minus Q, 40 plus K, times Q 40 plus T, which is the mortality rate. And the probability that was given of the death in year 1 would be Q40 is equal to 0.001. So the probability of death. in year 1. And now we have to, now the present value of death benefit in year 1 is just 200,000 times 0.001 times 1.05. That's the present value of death benefit in year 1. Now let me calculate the NSP by having all of the information. So we get 8,500 as an approximation. So the NSP would be equal to 8,500. Consider a life insurance company that offers a whole life insurance policy to individuals, age 50. The policy pays out a benefit of $100,000 upon death. The force of morality at age 50 is given by mu 50 is equal to 0.01, and it increases linearly with age such that ux is equal to 0.01 plus 0.001 x minus 50 for x is greater than or equal to 50. Assume that the force of morality is constant over each year of age, and that the interest rate is 5% per annum compounded continuously. Find the expected present value, EPV, of the insurance benefit for a policyholder age 50. So first, let me set up the EPV. So we have 100,000 over the integral of 0 to infinity of e to the negative 0.05 t mu of 50, and then we have plus t times e to the negative 50 plus t mu x dx over dt. So mu of 50 plus t is equal to 0.01 plus 0.001 t. Let me do 50 to 50 plus t mu of x dx is equal to the integral of 50 to 50 plus t 0.01 plus 0.001 times x minus 50 dx, and this is equal to 0.01 t plus 0.001 t squared over 2 is equal to 0.01 t plus 0.0005. Now let me figure out the EPV. So it would be 100,000 from 0 to infinity of e to the negative 0.05 t of 0.01 plus 0.001 t e to the negative 0.01 t minus 0.0005 t squared dt. 0 to infinity 0.01 plus 0.001t dt. The EPV is equal to 100,000 times 0 to infinity of 0.01, 0.001t e to the negative 0.6t minus 0.000t squared dt. And this is approximately 0.015. Now for the EPV is equal to 100,000 times 0.015, and that gives us 1,500. So the EPV is 1,500.
Let f of n to 1 to infinity be a sequence of non-negative measurable functions on a measure space x f of mu defined by f of x is equal to the lim inf as n approaches infinity of f of nx. Assume that f of n converges pointwise almost everywhere to a function f, that is, f of nx approaches f of x as n approaches infinity for almost every x. Assume that f of n is uniformly bounded in L prime, that is, there exists an m greater than 0 such that the integral of x f of nx du mu x is less than or equal to m for all n. Prove that the integral of x f of x d mu x equals the limit as n approaches infinity as the integral of x f of nx d mu x. So first, I'm going to prove that it's f of x versus uniformly bounded. So let me write a proof here. Since f of n x to f of x is almost everywhere, and given that f of nx is uniformly bounded in L, then I can apply the dominated convergence theorem. So the dominated convergence, or in other words, the DFT L prime. So if f of n approaches f almost everywhere, then there exists a g which is an integral function such that the absolute value of f of nx is less than or equal to g of x for all n and almost every x. Then I can show that also the limit as n approaches infinity of the integral of x f of n x d mu x is equal to the integral of x of the limit as n approaches infinity of f of nx d mu x is equal to This is equivalent to the integral of x, f of x, d mu of x. Since f of nx is, so we know that it is uniformly bounded in L prime, that means there exists an integral function g of x such that f of nx is less than or equal to g of x for all n with the integral of x of gx d mu of x is less than or equal to m. So we see that, therefore, using the dominance convergence theorem, we see that the integral of x, f of x, d mu x is equal to the limit as n approaches infinity of the integral of x, f of nx, d mu x. Let X be a norm vector space and let Y be a proper subset in X, be a subspace. Prove that Y is closed in X. Then the quotient of XY is a Banach space if and only if X is a Banach space. So first I need to prove that XY is a Banach space if and only if X is a Banach space. And I remembered that a Banach space is a complete norm vector space, which is a space where every Cauchy sequence converges to an element of the space. So first off, let me write down a proof. So we say that, let's assume X is a Banach space. And let sequence X of n be a Cauchy sequence in X, Y. Then this means that for all epsilon greater than 0, there exists a natural number n such that see that the norm between f of n and x of n is equal to the inf of yn in y such that see that the norm is less than epsilon for all m n is greater than or equal to n. We know that since X is complete and Xn is a Cauchy sequence, and X, which are the elements of Y, that means there also exists an X such that X of n of X is an X. Now I need to show that X of n goes to X. So it's an xy. So by the definition of
of the quotient norm, see that x of n minus x is equal to the infim of y and y, such that x of n minus x plus y. We know that since x of n approaches x, the infimum of, say, xn, this should be an xn, minus x plus y. So we see that it approaches 0, implying that you can see that the x of n approaches x in xy. And we see that also the quotient of xy is complete, meaning that it's a Banach space. Now that I showed that the quotient of xy is complete, which is a Banach space, I also need to show that the quotient of xy is a Banach, then x is a Banach. Now let's assume that xy is a Banach space. So let's say let xn be a Cauchy sequence in X. We know that since X is Cauchy, the sequence of equivalence classes, so let's say x of n, is also a Cauchy sequence in xy. And we know that since the quotient of xy is complete, that means there exists, let's call this an x, inside the quotient such that x of n approaches x in the quotient, meaning for all epsilon greater than 0, there exists a natural number n such that, take the norm space of x in x is equal to the inf of y of the norm space of xn minus x plus y is less than epsilon for all n greater than n. And then thus there exists a sequence y of n, which is a proper subset of y, such that we say that the norm minus x plus yn is less than epsilon, which shows that the sequence xn converges to x plus yn for some y, and in y.
And since y is closed, the sequence xn
Converges
to some
x.
thus
X is
complete. And therefore x is a Banach space. So now that I've shown that the quotient of xy is a Banach space, if and only if x is a Banach space, provided that y is closed in x. Let f of z and gz be two holomorphic functions defined on a connected open set, where the domain is a proper subset of C. Suppose that f of z is equal to g of z on a set E is the proper subset in the domain that has an accumulation point in the domain. Prove that f of z is equal to g of z for all C inside the domain. First, let me write down the proof. Let's consider one call is the set A, where C is in the domain and f of z is equal to g of z. Let me assume by hypothesis that E is a proper subset of A. Where also E is a subset of the domain. With a accumulation point in the domain. We know that since f of z and g of c, which are both holomorphic in the domain, so on the domain, their difference h of z is equal to f of z minus g of z is also holomorphic on the domain. And I also notice that h of z is equal to 0 for all z in A, since f of z is equal to g of z on A. That's why I put that there. And let me also denote that let z of 0 be inside a domain, which is a accumulation point. Accumulation point of E is a proper subset of A. Since h of 0 is equal to 0 on E and z of 0 is an accumulation point on E, and what I remember is by the identity theorem for holomorphic function, by the identity theorem for holomorphic functions, f of z must be 0 or identically 0 on for all inside a domain. Be identically
And the reason why is that since it's a holomorphic function is 0 on a set with the accumulation point, it must be 0 everywhere on the connected domain containing that set. Since h of 0 is equal to 0 on the domain, it follows that f of z is equal to g of z inside a domain, which I showed and proved the uniqueness of the analytic continuation in a connected open set. Let f be an analytic function on the open disk. D is where z is in the complex plane, and the absolute value of z is less than r, centered at the origin with radius r. Suppose that the limit as r approaches negative r of f of r e to the I data, and the limit as r approaches positive r of f of r e to the I data are equal and infinite for almost every data inside 0 and 2 pi. Prove that f extends continuously to the boundary the absolute value of z is equal to r. So first off, I would like to use the maximum module principle to prove this. So write down the proof. So first off, by the maximum modulus principle, for any r greater than r, the function f of z achieves its maximum value on the circle. So the circle would be represented by the absolute value of z is equal to r, where we have m of r is equal to the max of z is equal to r, so that's the absolute value of f of z, that's the absolute value of f of z, is equal to the max of data inside 0 to 2 pi of f of r e to the data. And also, given the condition we could also see that the lim sup of r goes to r to the negative is f of r e to the I data is equal to the lim inf as r goes to negative r of f r e to the I data for almost every data inside 0 to 2 pi. By L data, then the limit as r goes to negative r of f of r e to the I data is equal to L data for almost every data. Now I need to show that f of z extends continuously to the boundary z is equal to r. Since the limit as r goes to negative r of f r e to the I data is equal to L data exists and is finite for almost every data, and f of z is also analytic. The radial limit so we see that the limit exists for almost every data. Define a function, so let's call this g data is equal to the lim as r goes to negative r of f of r e to the I data. Since the modulus of f is bounded by L data, and L data is finite, f of r e to the I data does not exhibit any unbounded behavior as r approaches r. So hence the limit as r goes to r of negative r of f of r e to the I data is equal to g of data, which defines a continuous function on the boundary of f of z is equal to r. On the boundary with g data is equal to L data. Finally, since the radial limit exists and is finite, let's define the extension of f to a closed disk. So let me denote this as d, which is underline d, is z is in the complex plane where z is less than or equal to r. And by f of z is equal to the limit as r goes to negative r of f of r e to I data, where z is equal to r e to the I data. And thus f extends continuously to the boundary of z is equal to r. So now that I wrote this, I can see that the proof shows that the given connection on lim sup and lim if of an analytic function on a disk implies that the function extends continuously to the boundary of the disk. Let H be a Hilbert space and let T of H be a bounded linear operation. Assume that T is self-adjoint.
that is t is equal to t dash, where t dash is the adjoint of D. Prove that the spectrum T of T is contained within the real line. That is, the spectrum of T is a proper subset of R. So first, I'd like to write a proof, and I want to explain the self-adjoint operator for T. There's a proof. So for a self-adjoint operator T, if lambda is in C, is an eigenvalue of T with corresponding eigenvector. Let's call this X. Then T of X is equal to lambda of X. So let me denote this as T of X, X is equal to lambda XX. And taking the inner product with X on both sides, so we get lambda is equal to Tx X over X X. Since T is a self-adjoint, Tx is equal to T of X Tx. And we see that it is real, therefore the lambda must be real. The spectrum of T consists of those lambda for which T minus lambda I is not invertible. If we have a lambda which is in the spectrum of T and lambda is not in R, then T minus lambda I is invertible, which contradicts the assumption that lambda is in the spectrum of T. Therefore, it follows that T is contained within the real line. Let the domain be a proper subset of Rn, be an open-bounded domain, and W12 of the domain, denoted by H prime of the domain, be the Sobolev space, defined as W12 of the domain is equal to U is inside L squared of the domain, where U is in L squared of the domain raised to the n, where U denotes the weak ring of U. Show that there exists a C such that for all U is inside the Sobolev space, that the norm of U L squared inside the domain is less than or equal to C of the domain U of the Sobolev space, where the Sobolev norm is defined by U W12 of the domain is equal to the norm of U squared L squared of the domain plus the weak gradient squared of L squared of the domain n raised to the 1/2. So first I want to start off with this
Poincare inequality to prove this. So let me start off with a proof. So the Poincare inequality states that for a bounded domain and any function u is inside the Sobolev space with u is equal to 0 on the boundary that means there exists a CP that is greater than 0 such that we take the u norm of the integral function L squared is less than or equal to CP, which is the weak gradient of u, of the norm, L squared of the domain of n. And then however, if u does not necessarily vanish on the boundary, I can consider u minus u of the domain. So however, if u does not necessarily vanish on the boundary, I can consider mu minus mu of the domain, where u of the domain is equal to, basically this is 1 over the absolute value of the domain, of the integral of the domain of u dx. And it's the mean value of u over the domain. Then u minus u, the mean value of the norms L squared, is less than CP of the weak gradient of L squared of the domain n. So let me simplify from here. I use the mean value, which can be estimated using the Cauchy-Schwarz inequality. So that would be 1 over 1 omega over omega u dx is less than or equal to 1 over the domain which is just 1 over domain L squared of the domain. Now I can simplify more. Now this will become which implies that the norm of U is less than C of the norm squared plus the weak gradient squared which is just equal to C of U W12 over omega, or the domain, where C is some constant depending on C, P, and the domain. And therefore, I have established the desired Sobolev inequality that the L squared norm of mu or U is controlled by its Sobolev norm in W12 in the domain.
Let A be a C algebra and I be a proper subset in A be a closed ideal of A. Let A quotient of I denote the quotient algebra of A by I. Show that if J is closed ideal of A, then A, the quotient of the inverse of pi J, is isomorphism to A quotient I is quotient to J as C algebras. So first off, let me write down the proof.
Say, let J be a closed ideal of the quotient of AI. And let's define this as K is equal to inverse of pi J for A is in K and B is in A. And pi A is in J, and J is an ideal in AI. So this is equal to the pi of BA is equal to pi B times pi A, which is in J, and we see that pi AB is equal to pi A and also pi B, which is also in J. And hence, BA is in K and AB is in K. Then this is an example using the ideal property. Now I'm going to show using closeness. Now using closeness, if AN is a sequence in K such that AN approaches A in A, then pi AN approaches pi of A in A quotient I. Since pi of AN is in J and J is close, see now that pi A is in J, so hence A is in K, and now K is closed. Now I need to show that the A quotient of inverse of pi J is isomorphism to to also to A, which is the quotient of I, which is quotient to J. So let's say, well, let's define the map. Let me note this as just this to Aij. Let's say A plus inverse of pi j is equal to A plus I plus j. For a well defined if A plus pi inverse j equals B plus pi inverse j, then A minus B is in pi inverse 1j. So we see that pi of A minus B is in j, and hence A plus I minus B plus I is equal to pi A minus B, which is in j. And thus, A plus I plus j is equal to B plus I plus j. Using homomorphism, see that which is equal to which is also equal to A plus B plus I plus j. This is equal to plus inverse of pi j, and P of B plus pi inverse pi ij is equal to A plus I plus j B plus I plus j, and which is equal to A plus AB plus I. So for a bijective, every element in Aij can be represented as A plus I plus j, and it maps to every element. So it makes it a isomorphism. Therefore, for any closed ideal J of AI, inverse of pi j is a closed ideal in A, and we see that the A quotient of pi inverse pi of j is isomorphism to A I j.
Let X sigma algebra measure be a probability space, and let T of XX be a measure preserving the transformation. For a function f of L squared of the probability space, define the ergodic average. A of n f of x as n of f of x is equal to 1 over n, the summation of k0 n minus 1 of ft kx. Prove that if f is in L squared of the probability space, then a n f of n converges in L square norm on as n approaches infinity. First, let me write down L square norm is equal to the integral of x 1 over n, take k is equal to 1, n is minus 1, f of t k x squared e mu. We have 1 over n minus 1, k is equal to 0, f of t k x squared is equal to 1 over n squared, where we have k is equal to 0, n minus 1. We also have j is equal to 0 of n minus 1 of f of t k x of f of t j of x over this. And basically I'm expanding the square inside the integral. So simplifying more, get a of n f. So we take that norm, L squared is equal to 1 over n squared of n minus 1, where k is equal to 0, and also j is equal to 0 of n minus 1. Take the integral of x, f of tkx, we have f of tj x d measure. And then let me also write down, expanding some more, we have f of tjx d mu is equal to ftk f times tj, and using the fact that f of fj minus k, then we have an f L squared norm of n L squared equals n minus 1, k is equal to 0, of n minus 1, j is equal to 0, of j, or no, we have f of t j minus k. And then since f times dt j minus k is shifted by tj minus k, then I have an f squared norm is equal to n squared is equal to n squared, also n minus 1, k is equal to 0, and we also have n minus 1, j is equal to 0, of f 0 t j minus k. The double sum can be simplified using the fact that f of tm is 0 for m is not equal to 0 by orthogonality. We have f of n, f L squared norm is equal to 1 over n squared times n times the norm of L squared plus the lower order terms.
as n approaches infinity of 1 over n times the norm of L squared converges to 0. So a n f L's norm goes to approach 0. So hence we see that a of n f of x converges to 0 in the L squared norm as n approaches infinity.
Let x equal 2n be the Cantor space, which is the set of all infinite sequences of zeros, and is considered the Borel sigma algebra Bx on x. Show that the set A is equal to x of 2n of the lim of sup of n approaches infinity of x of n equals 1 is a Borel set in x.
So let me write down the proof here. So the set A is defined as the set of sequences. Call this x and 2n such that the sequence contains infinitely many, we'll say A, where x is in 2n, for all n inside n. That means there exists an m greater than n such that x of n equals 1. Let me also write down A is the intersection of n, and also the union of where m is greater than m. And basically I need to show that A is the Borel set. So each set is an open set in the product topology of 2n. We know that since the countable union of open sets is open, as well as the countable intersection of open sets is Borel. Therefore, we see that A is indeed a Borel set. In X.
Let M be a smooth manifold and f of m to R be a smooth function. Suppose that P is in M is a critical point of f, that is dP is equal to 0. Prove that if the Hessian of f at P denoted by fp, each of fp is non-degenerated, then P is a non-degenerated critical point, and there exists a local coordinate system x1, x squared, all the way to xn around P, such that f of x equals f of p plus 1/2 of the summation of I1 n of lambda I x squared, where xi are the eigenvalues of the Hessian HFP.
So first, let me write down the proof. I'm going to start off with non-degenerating critical points. Since P is a critical point, dFP equals to 0, which implies that the first order derivative of f vanishes at p. And basically the non-degeneracy of p means that the form, or the Hessian form HFP, is a non-degenerated bilinear form. And the bilinear form is a non-degenerated if its associated matrix in any basis has a non-zero. And now let me prove this also using Morse lemma. So let me see. Using Morse lemma, if P is a let's call it degenerated critical point of a smooth function, let's call this f, then that means there exists a y1, y2, all the way to yn, which is a smooth coordinate system around P, such that we could see that f of y is equal to f of p equal to 1/2 sigma squared of I is equal to 1 and epsilon to the I, where iy squared, where epsilon I is equal to plus or minus 1. And this corresponds to the eigenvalues. So it corresponds to the sign of the eigenvalues of the Hessian H of FP. And now I'm going to show it also by the diagonalization of the Hessian. And we also know that since H of FP is non-degenerate, that means there also exists a orthonormal basis in which the Hessian matrix is diagonal. So in the basis, the local expression of f around p is f of x is equal to f of p is equal to 1/2 times the sigma squared of n I is equal to 1 of lambda I, where we have x I squared, where see that lambda I are the eigenvalues of the Hessian. And now that I can see that the local coordinate system can be chosen such that the function f takes on the form where we see that the eigenvalues I of the Hessian h of fp is the non-G generation of P, which ensures that these eigenvalues are all non-zero, showing that P is a non-G generated critical point. Consider the heat equation. U1 is equal to delta U in the domain of 0 and T, where the domain is a proper subset in R and is a bounded domain with a smooth boundary of the partial of the domain of U of the domain of 0T in R, and U1 is equal to the partial of U to partial of T, and delta U is equal to the summation of ij to n of the second partial of U with respect to xi squared is the Laplacian of U. The function u xt represents the temperature at point x, which is in the domain, and time t from 0 to t. The initial condition u x0 is equal to u0x, where x is inside the domain, and u of 0x is a given initial temperature distribution. Suppose we have a homogeneous Dirichlet boundary condition u xt is equal to 0, where x is a partial inside of domain, and t is 0 to t. Show that the heat equation is well in the sense of the Hadamard. That is a unique solution that depends continuously on the initial data u0x. So first, let me write down the formulas. Ut is equal to u, which is in basically what's given. So first, if u0 is into L squared of the domain, then there exists a unique solution, let's call it u, which is in the time, so L squared domain, such that and u1 is an L squared 0t of inverse of h of the domain. And now I can prove by uniqueness, and let's assume that there are two solutions in uxt. So let's say vt is equal to delta v inside the domain of 0 and t, we have v of x0 is equal to 0, where x is inside the domain. I'll say there is two solutions where u is uxt and u2xt, which satisfies the heat equation with the same initial data. And considering their difference is v is equal to u1 minus u2. So let me write that down. Where x is inside its domain and t is 0 to t. And now I can write this as an integral of vt and v dx is equal to the integral of the domain delta v times v dx. And this is an energy method, and basically I would multiply the partial differential equation by v and integrate over the domain. So from here we get 1/2 Take out the 1/2, and then we have d dt of the integral of the domain v dx. And then simplifying from here, get delta v times v dx is equal to the negative integral of the domain v squared. And now the right hand side, we can see that it can be rewritten using the integration by parts and using the boundary conditions v is equal to 0 on the partial of the domain. So now we have d dt, which is the domain of v squared dx plus 2 of its domain, taking dx is equal to 0. And now this is d dt of the integral of v squared dx is less than 0. So let me write down u01, q20, which is inside the L squared norm of the domain, b two initial data sets, and let u1xt and u2xt be the corresponding solutions. And let's define W is equal to U1 minus U2. Then W satisfies WT is equal to delta W in the domain of 0 and t. Now we have Wx0 is equal to U10x minus U02x, where x is inside the domain. So Wxt is equal to 0, where x is inside its partial domains, and t is 0 to t. And one standard method for proving existence is, there's a method called the Galerkin method or energy method. And for simplicity, I can also rely on the well-known result for a heat equation. So I would use the energy method here, in this case. So half d dt is the domain of w squared dx is equal to negative integral of the absolute value of the w dx. And this is, I can use the energy. This is called the energy method. So now, from here, I can use d dt of the domain of w squared dx is greater than or equal to 0. And now let's take the boundaries of w squared x t dx is less than or equal to the domain of w x0 dx is equal to the integral of the domain of u0x minus u0 n. So we have that squared dx. And this shows that the solution u of x depends continuously on the initial data u of x0 in the L square form. So it's this right here.
Consider the initial value for the wave equation on a bounded domain with smooth boundary, where u t t x t is in delta t x t of the bounded domain where t is greater than 0. Have u x0 is equal to u0 x, where u t of x0 is equal to v0 of x, where x is inside the domain. We have u x t is equal to 0, where x is in the bounded domain, and t is greater than or equal to 0, and where u0 v0 is within h prime 0 of the domain. Show that the wave equation can be formulated as a first order system, and that this system generates a strongly continuous semigroup on the Hilbert space. So I would like to write this as a first order system. So let me write down ut is equal to w, and wt is equal to u. And this is a first order system, so the wave equation is a second order partial differential equation, or PDE, in time. And to use semigroup theory, I will rewrite this as a first order system by sorting a new variable. First off, I will denote this as d dt as uw is equal to 0I delta 0. We have uw, where I is the identity operator. So let me define the operator A. So we denote this as AUW is equal to W delta U. And this is the operator A on the Hilbert space. So we would denote this as H0 prime domain times L square function of the domain. And this would be represented by d t over u w is equal to a u w, u w 0 is equal to u0 v0. And this is a system now is on an abstract Cauchy. So based on the generation of semigroup, so we say that the operation A generates so we say the operation A generates a strongly continuously semigroup. We call it T of T on the Hilbert space, which is denoted as this. This follows from the fact that A is skewed adjoint, which is just A is equal to negative A. And we see on this space, which guarantees that A
it generates a unitary, or in other words, strongly continuous semigroup. Consider a smooth Riemann manifold MMGT, where GT is a one-parameter family of the Riemann metrics evolving under the Ricci flow, which is given by the formula by partial with Gij over partial d. T is equal to negative 2 RCIJT, where Ric IJT is the Ricci curvature of the metric GT. Consider the round metric G0 on S2 a constant positive curvature. Show that under the Ricci flow, this metric evolves by scaling, that is, GT is equal to 1 minus 2 lambda T G0 for some lambda is greater than 0. So first, let's consider the round metric G0 on S squared with constant positive positive scalar curvature. So let's say R is equal to 2K. And under the Ricci flow, we would get and for a round sphere, the Ricci tensor is given by RICIJ is equal to KGIJ, where K is the Gaussian curvature. So let me write that down here. And now let me simplify using simple scaling equations. And I can see that for lambda is equal to k is the curvature, and the metric remains in the conformal class, and just scaled by a factor that depends on time. So as t increases, the sphere shrinks uniformly, and the metric will collapse to a point as t approaches 1 over 2k. And this shows that the behavior of the Ricci flow on a round sphere, illustrating how positive curvature causes the metric to contract uniformly over time. Let U be in L squared of Rn be a function in the Sobolev space, where H prime of Rn, is the space of functions in L square Rn, whose first derivatives are also in L square Rn. Prove the Sobolev inequality in Rn for U inside the space of functions. That is, show that there exists a constant c is greater than 0 such that the norm of U of L squared of Rn is less than or equal to c of the norm of U H prime of Rn, where 2 is equal to 2n over n minus 2 if n is greater than 2 and 2 is equal to infinity if n is equal to 2. So I'm writing down the proof here. So given that mu is an H inside the space of functions, and U is a function in the Sobolev space, and we have U is inside the norm by the Galliardo-Nirenberg Sobolev inequality. I can prove this. So basically we have norm of U L squared of R to the n is less than or equal to c And now let me write this as u L squared Rn is less than C less than Rn. And then, however, we can see that gradient of u L squared Rn is part of the Sobolev norm, which in this case it's u h1 of Rn. So therefore, for all u inside the space, inside the space of functions, there exists a constant c greater than 0 such that the norm of u L squared of Rn is less than or equal to c of the norm of u of Hrn.
Let f of L squared of Rn be a function. Consider the Littlewood-Pauli square function s of f defined by s of fx is equal to the integral of 0 to infinity of x times the curve 1 of x squared dtt to the 1/2, where the curve of 1x is equal to t to the negative n curve of x over t for some fixed function curve, with r is equal to the curve x dx equals 0. Prove that there exists a constant c greater than 0 such that the norm of f of LPRN is less than the norm of STLPRN, for p is between 1 and infinity. So let me write down the Littlewood-Pauli square function formula. So we denote mf is equal to x is equal to the supremum of r, where r is greater than 0, take the integral of brx f of y dy. And I can use the fact that the Littlewood-Pauli square function s of s can be related to a maximal function. And basically, I let mf be defined by the Hardy-Littlewood maximum function, and it's defined by this, where brx is the ball of the radius r centered at x, and the brx is its volume, or the absolute value of brx is its volume. So using the Littlewood-Pauli theory for functions f of LP Rn, where p is between 1 and infinity, it is known that the norm of s of f LP of Rn since the Hardy-Littlewood maximum M is bounded on
LP Rn for P is between 1 and infinity, there exists a C or a constant C such that the f of L, norm of f, take the norm of f, LP of R of n. And now basically I can combine the results. So now we have f of LP is less than C. It's also S of f LP Rn. And basically where the constant C depends on P and N, but not on F. Consider the domain D is equal to Z1, Z2 inside the complex square is equal to Z1 squared plus Z2 squared is less than 1, which is the open unit ball on C squared. Let F of the partial domain of C be a continuous function on the boundary of D, where partial D is equal to Z1, Z2, which is then C squared is equal to Z1 squared plus Z2 squared equals 1. Using Hartogs theorem, show that if F is holomorphic on a neighborhood of partial D and bounded, then there exists a holomorphic extension of T of F to the whole domain D. So Hartogs theorem applies to domains in Cn where n is greater than or equal to 2. In this case, the domain D is an open subset of C squared. The function is given to be holomorphic on a neighborhood of D, partial D, and bounded. So let me write down a proof here. So using Hartogs theorem, if F is holomorphic on a neighborhood of D and bounded, it can be extended to a holomorphic function on the entire domain D. Specifically, since the boundary D is a complex manifold of dimension 1 and D is of dimension 2, F can be extended from partial D to D, using the fact that holomorphic functions in several variables extend from a boundary of sufficiently high codimensions. Let omega be the domain in C squared defined by the domain of Z1, Z2 in the complex plane C squared, where the real of Z1 is greater than 0, and the absolute value of Z2 is less than 1, where the domain is a product of the right half plane in C with the open unit disk in C. Given a compact set K, which is the proper subset in the domain, show that there exists a holomorphic function on the domain that achieves its maximum on K.
So let me write down a proof here. So let K be a proper subset of the domain, be a compact since that the domain is holomorphically convex, any compact set or subset K will have a holomorphically convex hull that is contained within the domain. So let's consider the holomorphic function. Let's call this fz1, z2 is a real 1 over the real of z1 times 1 over 1 minus z squared 2. See that the function is holomorphic on the domain, since we see that the real of z1 is greater than 0 and the absolute value of z2 is less than 1. This function f is bounded on compact subsets and achieve its maximum on K on a compact subset K of the domain. The function f also attains its maximum value since K is compact and f is continuous. On the domain, and the holomorphic convex hull of K will be contained within the domain due to the convexity of the domain. So we see that the holomorphic function, function f satisfies
the condition
of achieving its
maximum
on K, thus showing or demonstrating the holomorphic convexity of the domain. Let the domain be a proper subset of Rn be a bounded open domain with a smooth boundary. Consider a compact set of the boundary. Let U be a non-negative Borel measure on the domain. Show that the Bailliac measure on U onto domain is a finite Borel measure on the domain. So let me write down the proof here. So for a point x inside the domain, let W x dot be the harmonic measure with x, which is a probability measure on the domain that describes the distribution of Brownian motion starting at x and hitting the boundary which is the domain. So let's say we have, I want to write down the Bailliac method measure V. So V is equal to the integral of the domain Wx b du x for any Borel set we have inside that domain. And then to prove that V is a finite measure, I need to show that V is finite. So let me write down V is in the domain of the integral of the domain of W x since W x, which is in the domain, is a probability measure on the domain. So W inside the domain is 1. So V would be equal to W and since U is a non-negative Borel measure
the domain, and the domain is bounded, we see that U is finite on the domain. Thus, this shows that U, the domain, is less than infinity, and that V of the domain is equal to U of the domain is less than infinity, which shows that V is finite on the domain. On the domain.
Let n be a differentiable manifold of dimension n. Consider the smooth map f of n to rk given by f of p is equal to f1p, f2p, all the way to fkp, where each f of mr is a smooth function. Prove that the differential dfp tpm to rk is a linear map.
So first I need to prove that dfp is a linear map. So write down the proof. So the differential dfp of the map f at the point p is m is defined by dfp fp to rk. So dfp v is its partial with respect to x of p times v. Take its second partial derivative with respect to x of p times v, all the way to p, its partial derivative with respect to x of k, p times v, where v is in TPM, and TPM is basically the tangent space. It's the tangent space to M at P. And we see that the map DFP is linear since it's defined as a derivative, which is inherently linear. For any v1 and v2 inside the tangent space, and any scalars a, b, and r. So we have dfp is a v1 plus b v2 is equal to ADFP v1 plus BDFP v2, which follows directly from the properties of the derivative. And we see that the differential dfp, the tangent of mrk, is a linear map. Consider the action of a discrete group of the gamma of a homogeneous space x is equal to g
of the lattice, where G is a Lie group and lattice is a lattice in G. So let f be a square integral function on x, that is f of L squared of x. Using the mean ergodic theorem, show that the time average of f under the action of gamma converges in the L squared sense to a function that is invariant to the action of gamma. Specifically, prove that the sequence of averages a n f of x equals 1 over n. The summation of t, y, n f of x converges to L squared m to a function f to infinity to L squared n that satisfies t, y times f infinity equals f infinity for all gamma inside the space. So the mean ergodic theorem states that for unitary operator t on the Hilbert space H1, the time averages of the iterate of t converge in the norm of H to the projection of the initial function onto the space of t invariant functions. So let me write down a proof here. So t is unitary on L squared H. And the space of t invariant functions is given by this, the integral square function for all gamma inside the gate. So using the mean ergodic theorem, states that the sequence of averages a n f of x is equal to 1 over n of n is equal to n is equal to 1 of t and f of x converges in L square x to a function of 0 that lies in the invariant, which is t f0 is equal to f0. So now that it lies inside, then I showed using the mirror ergodic theorem that the sequence converges. Let x equal P1, the projected line over an algebraically closed field at K, and let K of OX1 denote the twisting sheaf on P1. Consider the quasi-coherent sheaf F is equal to OX1. Show that F is quasi-coherent and find the global section H0 of XF. So let me write on a proof here. So we see that the sheaf OX1 is quasi-coherent since OXN for any integer n is locally free sheaf on X. The global sections of OX1 corresponds to
homogeneous polynomials of degree 1 in the homogeneous coordinates. So we call this x0 and x1 on P1, which are in the linear forms ax0 plus bx1, where a, b is in K. So therefore, you see that the global section of OX1 is isomorphism to K decomposition of 2. Let X equal P1K be the projected line over enclosed field K. Consider the line bundle OX negative 2 on X. Show that HIX OX of negative n is equal to 0 for all n is greater than or equal to 1 and I is equal to 0, 1. So let me write down the proof. First, I want to show off for h of 0 x OX to the negative n. So for n greater than or equal to 1, the global section HO of x of 0x to the negative n corresponds to homogeneous polynomials of degree negative n. That is h0 h x of OH x to negative n equal to 0. Since negative degree polynomials do not exist. Now let me do it for h1x. So for h1 x OX to the negative n. So I could use serial duality, that h of 1, see that it's isomorphic, or isomorphism to h0 of OX0 n minus 2. So if n is greater than equal to 2, then we see that n minus 2 is less than 0. So h0 of x OX n minus 2 is equal to 0, which implies that h1 x of OX negative n is equal to 0. So thus, for all n greater than or equal to 0, h0 of x0 OX of negative n is equal to 0, and h1 x OX of negative 1 is equal to 0. Consider the family of Riemannian manifolds T of n, G of epsilon, where T of n is equal to Rn, which is the quotient of SC, is the n-dimensional flat torus equipped with the Riemannian
metric g of epsilon where epsilon squared g0, where g0 is the standard flat metric on t of n, and epsilon is greater than 0, is a small parameter. Prove that the family t n g epsilon converges in the Gromov-Hausdorff sense to a single point epsilon approaches 0. So specifically show that the Gromov-Hausdorff distance between Tn and g of epsilon and a point as a metric space tends to 0 as epsilon approaches 0. So first off, I want to start off with a proof on the Gromov-Hausdorff distance between two metric spaces. Here's the proof. So the Gromov-Hausdorff distance dgh of xy between two metric spaces x and y is the infimum of the Hausdorff distance between their isometric embeddings into a common metric space Z. So let's denote this as, I would denote that d of gh of xy is equal to the infimum, let's call this d of h, where we have the curve of x to x with respect to x, and also with y, where we see that curve of x maps to z, and also with y, also let me put down here x and y here, don't forget that, are basically, these are isometric embeddings. And dh denotes the Hausdorff distance. Let's consider Tn g epsilon and a point space. Let's call this P, which is just a single point metric space as C. So let's embed T of n g of epsilon into a common metric space in a way that the image of Tn under
G of epsilon becomes arbitrarily small. As epsilon approaches 0. So that means we have the Hausdorff distance, Gromov-Hausdorff distance of the curve of epsilon of Tn and P is equal to, basically it's the half times the diameter of Tn G of epsilon. And we see from simplifying here, we get a half times epsilon of d0. And the Hausdorff's distance between the embedded, the curve epsilon to Tn, and the point P. And that's a diameter, basically. So as epsilon approaches 0, we see that the Hausdorff distance tends to go to 0. And since the Gromov-Hausdorff distance d of g h goes to 0, as epsilon goes to 0, I can conclude that Tn G epsilon converges to a point space in the Gromov-Hausdorff sense.
Find the cohomology groups H of n x for the space x is equal to RP squared, where it's known as the real projective plane. So before I find the cohomology groups, I like to point out what the real projective is. So the real projective, or RP squared, is a space of lines through the origin in R cubed, or equivalency, the quotient space of the two spheres S squared under the equivalence relations that identify antipodal points. Also, the real projective plane has a cellular decomposition with 0 cells, which is a single point, 1 cell on edge, and 2 cell, which is a disk. And given the cellular decomposition, I can find the cohomology groups using the cellular chain complex cellular chain for the real projective plane. So let me write down. This would be known as C2, C1 to Z0 to 0, where Z0 is generated by the Z0 cell, one-dimensional vector space. So Z0 is isomorphic to Z. C1 is generated by the 1 cell, which is one-dimensional vector space. So C1 is isomorphism to Z, and Z2 is generated by the 2 cell, which is one-dimensional vector space. So C2 is congruent to Z. And let me write down the boundary maps. So you see that the first map maps the 1 cell to the 0 cell, and also
we have the second cell, we have C2 to C1, which maps the 2 cell to the 1 cell. But since the 1 cell is in the real projective, is not a boundary of the 2 cell, but instead is mapped to itself with a orientation that reflects the identification of the antipodal points, the boundary map for 2 for the real projective is actually a map that senses the 2 cell to itself with a factor of 2. To define the cohomology group, I would use the dual chain complex, where Z0 is the dual of C0 and Z is in Z, and C1 is the dual of C1 and is C, and Z2 is the dual of C2 and is in C. So basically it would be written as this. C2 all the way. And the whole cohomology group, I would write the formula down. It would be H of n RP squared is equal to the kernel of its mapping, whatever n is, of the real image of n minus 1. So let me plug in 0 here. We see that H0 of RP squared is equal to the kernel of 0 is equal to and basically the boundary map 0 is a trivial map. So let me do n is equal to 1. So H1 RP squared is equal to and the boundary map 1 maps the 1 cell to the 0 cell, and due to the identification of the antipodal points, the map is surjective, and the image of the map 0 is 0. So H1 RP squared is isomorphism to Z squared. So we see that also. See that H1 RP squared is isomorphism to C2. So let me plug in n is equal to 2 here. So H2 RP squared is the kernel and we see that the boundary map 2 maps the 2 cell to the 1 cell with a factor of 2. In the image of the boundary map 1 is Z, since the 1 cell boundary is mapped to 0. So H2 of RP squared is isomorphism to C. So C2 RP squared is isomorphism to C. And now let's do for n is greater than 3. So since RP squared is a 2-dimensional space, we see that H of n RP squared is equal to 0. And the cohomology group R0. So we see that Let me write down everything here. So we see that H0 RP squared is isomorphism to Z for H1 RP squared is isomorphism to Z squared. H of 2 is RP squared is isomorphism to Z. And for, call it H of n, RP squared is equal to 0 for n is greater than or equal to 3. So these are the cohomology groups, H of n, x for the space in the real projective plane. Let X be a topological space that has a filtration by closed subspaces. We have X0 is a proper subset of X1 all the way to Xn is equal to X. Assume that each inclusion Xi minus 1 to X is a covibration, and let Y of I equal X of I, which is the quotient of X minus 1, be the associated quotient spaces. Consider the associated spectral sequence ERPQ of the homology of the filter space X converging to the homology H of X, Z of X. The E1 page of the spectral sequence is given by E1PQ is equal to HP plus Q of YPZ, with differentials of E1PQ goes to E1P minus 1Q. Find the E page of the spectral sequence for the space X, assuming that each Yi is a homotopy equivalent to S squared. So let me figure out what E1 page is. Basically, that would be H of K, Yi of Z. Let's say it's isomorphism to Z if K is equal to 0 or K is equal to 2. Given that Yi is a homotopy to S squared. In other words, Yi is a homotopy to a 2 sphere, so the homology groups of Yi are this and 0 otherwise. So let me figure out E1 PQ. It's just H plus P plus Q of YP of Z, which is isomorphism to, call this Z and 0 if, say, Q is equal to negative P or Q is equal to 2 minus P and 0 otherwise. So this is how we figure out what E1PQ is for this. And thus, we see that the E1 page has non-zero entries only when P plus Q is equal to 0 or P plus Q is equal to 0, and it continuously keeps on going. Let L0 and L1 be two transversely intersecting Lagrange manifolds in a symplectic manifold, MW. Consider the Floor chain complex CF L0, L1 generated by the intersection points P1, P2 all the way to Pn of L0 and L1. Show that the Floor chain complex CF L0, L1 with the differential defined by counting holomorphic strips, that is maps U of R to 0 to 1 to M, satisfies the Floor equation, is indeed a chain complex, meaning that the differential satisfies partial D squared is equal to 0. So first let me define the Floor chain complex. There's the proof. So the chain complex CF L0 L1 is generated
by the intersection points P1, P2, all the way to Pn of the Lagrangian submanifolds L0 and L1. And the differential CF L0 L1 to CF L0 L1 is defined by, for each generator of Pi, we take the differential of Pi is equal to the summation of Pj of MPi Pj times Pj, where MPi/Pj is the module space of the holomorphic strips, satisfying the Floer equation connecting Pi to Pj, and module space is the algebraic count of these strips. So now I'm going to write down the moduli space. Here's an equation. Where the moduli space consists of holomorphic strips that solve the Floer equation. So that's why I wrote this down. And J is a compatible, almost complex structures on M. Now I also need to prove that the differentiable squared equals 0. So let's consider the composition differential of Pi so this would be so say I and Pj times Pj, and then I can expand this. And now I can see that the moduli space of the holomorphic strips with boundary conditions on L0 and L1 and connecting Pi and Pk can be compatified. The boundary lines on this compatible module space, which correspond to the broken strips, which can be viewed as two strips which are one connecting from Pi to Bj and are connected to Pj and Pk. And also the broken strips represent the composition of the differential, so the boundary of the module space of strips connecting Pi to Pk corresponds to the contributions from the differential squared. So since the boundary of the moduli space is compact, and consists of broken
strips the algebraic count of boundaries is 0, implying that the sum of contributions to the differential squared of pi must cancel. So they have to cancel out, where we have the differential squared is equal to 0. Therefore, the floor chain CF L0 L1 is a chain complex.
Let M be a smooth closed-oriented manifold, and let f of nr be a function, that is, a smooth function whose critical points are non-degenerated. Suppose P1, P2, all the way to Pk are the critical points of f, with corresponding indices of independent of P di is equal to ipi. Show that the number of critical points of f of index I denoted by MIF satisfies the weak Morse inequality, that is, the MIF is greater than or equal to the rank HI, where MZ, where HIMZ is the ice homology group of M with integer coefficient.
So let me set up the Morse complex. So here's a proof. We have CIF is a decomposition of the independent PJ is equal to I Z times PJ. So the Morse complex CF is defined by taking the free abelian group generated by the critical points of f of index I. So let's say the differential CIF to C I minus 1 F counts the number of gradient flow lines, which is module 2, connecting critical points of index I to critical points of index I minus 1. And now I need to set up the chain complex in homology. So the Morse complex let's note this C F of its differential forms a chain complex, which is just the differential of I minus 1 and the differential I is equal to 0. The homology of the chain complex call this HI is isomorphic to the singular homology so it's H of I M C of the manifold M. And now the rank of the weak Morse inequality or the ith homology group H of I M C is the dimension of the quotient so we call it the kernel of the differential of I and the real of the differential of I plus 1. So therefore, the rank of HI of MZ is less than or equal to the rank of kernel of the differential I is less than the rank of CI T, which is equal to MIF. And this proves the Morse inequality. So MIF is greater than or equal to the rank of HI of MC.
Let G be a compact Lie group, and let L squared G denote the space of square interval functions on G with respect to the Harem measure. Consider the regular representation of G in L squared G given by LGFX is equal to F inverse G of X for Gx inside G and F L squared G. Show that the space L squared G decomposes as a direct sum of infinite dimensional irreducible representation of G. That is proof that L squared G is isomorphism to the direct space sum of pi in G of V pi, which is the tensor product of V pi, where G hat is the set of equivalence classes of irreducible representations of G. And V pi is the space of the irreducible representation pi, and V pi is the dual space.
So the first to start off with the Peter-Weyl theorem, and it states that if G is a compact Lie group, then the space L squared G of square integral functions on G decomposes as a direct sum of the spaces corresponding to irreducible unitary representations of G. Let me also note that L squared G is isomorphism to the direct sum of pi G of the dimension pi times pi, where G hat denotes the set of all equivalent classes of irreducible unitary representations of G, and the dimension of pi is the dimension of the representations of pi. So let me start to write a proof. So for each irreducible representation pi So let v pi be the vector space on which pi acts. And you see that the representation space v pi is finite dimensional, and the space v pi is the dual space of v pi, which consisting of all linear functions on v pi. And what I mentioned is that the Peter-Weil theorem further refines the composition by showing that L squared G is isomorphic to the direct sum of tensor products, which is L squared G is isomorphism to pi G of v pi, which is the tensor of v pi. And we could also see that this v pi, which is tensor of v pi, represents the space of matrix coefficients of the representation pi I. And now we could see that the isomorphisms given by associating a function f of L with its Fourier coefficient of f with respect to pi, which is an element of v pi. The map f to, which is a summation of pi to g of the dimension of pi times pi of f, where pi of f is the projection of f onto pi component, which provides the decomposition. So you see, therefore, prove that the space of a square interval is isomorphism to the direct sum of pi g of v pi Tensor of V. So basically the space of the matrix coefficients of pi.
Let R be a ring and let M be a module over R of finite length. Suppose that M can be decomposed into two different sum decompositions. M is equal to M1, M2, all the way to Mn is equal to N1, N2, all the way to Nm for each I and j. Show that N is equal to M. That is the number of I in decomposition sums in decomposition must be the same. So first, I would start off with a proof using the fitting lemma. I'm going to talk about that. The proof here. So using the fitting lemma for any module homomorphism up to mm, where m is finitely call this m is equal to the kernel of fk, which is its sum decomposition of IMFK. And M can be decomposed as this composition, which implies that every endomorphism of a finite length module can be represented in a block diagonal form corresponding to decompositions or decomposable components. For some integer since M has finite length, each summand mi and mj also has finite length. Say we have m equals m1 plus m2 all the way to mn. Then we also is equal to n1 n2 then we have all the way to nm. And basically the length m of m is the sum of its length of its e in decomposable components. We have m here. I have an m here. Should have another m. All right. So now we have that. Since m1, m2, all the way to Mn, and N1, N2, all the way to Mm are indecomposable. Their lengths must all be positive integers. Let's assume n is not equal to m. So without loss of generality, let's assume n is less than m. And this applies that more summits or this implies that the decomposition m is equal to n1, decomposition n2, all the way to the sum product of mn has more summits than m is equal to m1 let's say let fmm be an R module endomorphism that maps each mi to 0. For all I, it is the identity of nj. Or on nj. And then according to the fitting lemma, so according to the fitting lemma, we can see that, I can also see that m can be decomposed for some r. So let me write down m is equal to the kernel of fk, and it can be the sum that can be decomposed for some k. But by the construction that I made of f, see that kernel of fk is equal to m, and im fk is equal to 0, which shows that m is equal to the kernel of fk, implying that So we take that without non-trivial. Image. And basically this contradicts the initial assumption that the mi are non-zero. So this contradicts the initial assumption that the mi are non-zero and indecomposable. So furthermore, by the uniqueness of the Krull-Schmidt theorem, each mi must be isomorphic to some mj, and therefore prove that m is equal to m. Let G be a connective reductive algebraic group over a finite field FQ with a corresponding Frobenius f of GG. The fixed point GF is known as a finite group of Lie type. Let P be a parabolic subgroup of G, that is F stable. Prove that PF is a subgroup of GF. So iron down the proof here. So the set PF consists of elements P such that FP is equal to P. But I need to show that PF is closed under the group operation. That is the multiplication and inverse. So let P1, P2 be in PF. Then FP1 equals P1 and FP2 equals P2. So let's also consider the product. And since F is homomorphism, we see that F of P1, P2 equals F of P1 times F of P2, which is equal to P1 times P2. And therefore, see that P is in, we could see that P is in P1, well, P1 and P2, showing closure under multiplication. And now let P be inside PF, then FP is equal to P. And now I'm going to consider the inverse. Call it P negative 1. We know that since F is a homomorphism F of P1, inverse of P, is equal to F of P, negative 1 is equal to inverse of P. So therefore, inverse of P is equal to PF, showing closure under inversion. And therefore we see that PF is a group. Or is a subgroup of GF. Consider a two-dimensional conformal field theory on the complex plane C with coordinates C and complement C. The theory has a holomorphic stress energy tensor Tz and an anti-holomorphic stress energy tensor Tz. The conformal word identities describes how the correlation functions of primary fields of Zi transform under infinitesimal conformal transformations. Given the following data, the stress energy tensor Tz satisfies the operator product expansion, or OPE, of TZ-TW is about C over 2 over C minus W to the fourth plus 2TW over Z minus W squared plus the differentiation of TW over Z minus W, where Z is the central charge of the theory. The primary field ZZZ with conformal dimensions HH satisfies the OPE. TCWW is approximate H of WW over Z minus W squared plus the differentiation of W with WW of Z minus W. To derive the conformal word identity for the 2-point function ZZ1 of ZD2 using the OP of the stress energy tension TZ with the primary fields. So let me write it down. So first, you have TZ is WW. It's about H W over C minus W squared plus we see that given the OPE between TZ and the primary field, the 2-point function is affected by a conformal transformation. So let me write down the conformal word identity states that TZ1 of 2 C2 is basically equal to Ci is equal to 1 Hi of Z minus Z I squared plus 1 over Zi is also its partial of theta 1 and now I can use the 2-point function on primary fields. So let me write this down. And I'll show you, I'll derive the
from a word identity for this problem. So it'd be this. So using the fact that the 2-point function of primary fields takes on the form, and I can derive the word identity by considering how TC acts on this function. And the 2-point function is non-zero only if H1 is equal to H2. Let R be a commutative ring. Assume that R is a finite direct product of local Rn rings, as R is equal to R1 times R2 times all the way to Rn, where each Ri is a local Rn ring with maximal ideal Mi. Show that for each I, there exists an idempotent element EI in R such that EI squared is equal to EI and EIR is equal to RI, where EIRJ equals 0, for J is not equal to I. So let me write down the proof, what's given. So given that R is equal to R1 times R2 all the way to Rn, let's define the idempotent. Let's call this, I call this EI is equal to 0, 0, 1, 0, where 1 is the ith position and 0 in all other position. And now let me define EI squared is equal to and taking the product is equal to which is equal to EI. And now I have to check that EI is an idempotent by verifying idempotent property. So thus, EI satisfies EI squared is equal to EI. And now let me consider a projection onto Ri. So let me consider the module EIR is equal to, let's say, EI times R1, R2 all the way to Rn. And we have also R1, R2 all the way to Rn is in R. And this is equal to 0, 0, 1, 0, where Ri is in Ri. And I can see that the set of elements corresponding to Ri in the direct product R times all the way to Rn. So EIR is isomorphism to Ri. And for Ji, or zeroing out other components, I can see that ERIJ is equal to EI times R1, R2 all the way to Rn, where RJ is in RJ, which is just 0, 0 all the way to 0, and it's equal to 0. So therefore, thus, EIRJ is equal to 0 for all j is not equal to I.
Consider a vertex algebra V with a state field correspondence y minus z and a vacuum vector 1 satisfying the axioms of vertex algebras. The modes of the vertex operator are denoted by yaz is equal to the summation of n and z, where an is equal times z negative n minus 1 for any a and v. Given two elements a, b, and v, use the locally axiom Borcher's identity to derive the commutator formula for the modes dm and bn, where am bn is equal to the summation where k is greater than or equal to 0 of mk, choose mk, of akm of m plus n minus k, where akb denotes the case product of a and b in the vertex algebra.
So let me state the locally axiom. For a vertex that for any a, b, and v, there exists a natural number n such that we see that y, az, b, w is equal to 0. Now I can expand y, az, y, b, w is equal to the summation of mn and z, and then we see that we have am and bn is equal to z n minus 1 of w negative n minus 1. So expanding the vertex operating in modes, the locally condition implies that the commuter yaz and ybw is a Laurent series in z minus w, and this gives the commuter formula for the modes. So basically, we have am bm is equal to the summation of k is greater than or equal to 0 of mk of akb, where m plus n minus k. And this formula shows how the modes of the vertex operators interact, and it captures the algebraic structures of the vertex algebra.
Let V be a finite dimensional vector space over an algebraically closed field C of dimensions n, and let TKV is equal to V tension product K be the K tension power of V. Consider the natural actions of the general linear group GLV and the symmetric group SK on TKV. Consider V is equal to C squared and K is equal to 2. Find the decomposition of T squared V is equal to VV under the action of GLV times S2. And identify the irreducible components corresponding to the Schur Y duality.
So what's given is that given V is equal to Z squared and K is equal to 2, then T squared V is equal to V of its center product of Z squared of Z squared. And we see that S2 has two irreducible representations and sign representation, and the tensor space decomposes into symmetric and anti-symmetric parts. Well, you could also see that t squared v is equal to the symmetric squared of v, which is the sum decompositions of L2v. And let me talk about what symmetric 2 squared v corresponds to. The trivial representation of S2 and is a three-dimensional irreducible representation of GLV. So AL2 squared V, or alt squared V, corresponds to the sign representation of S2 and is a one-dimensional irreducible representation of GLV. And now let me use under Schwarz-Watts duality. Let me identify the reducible components. So we have t squared v is isomorphous to v2, taking its tensor product of S2 and its decomposition sum v11 and its tensor product of S11, where v2 is equal to equals the trivial representation of S2 of v, and v11 equals the sign representation of S2. And it corresponds to the partitions two and one of 2 respectively.
Let V be a vertex operator algebra VA, and let G be an automorphism of V of finite order n. Consider the twisted V module MG corresponding to the automorphism G, and let M be a untwisted V module. Show that if V is a rational VA, the Q trace ZMVT is equal to TRM VQ L0 minus C over 24 is a module form of a certain weight. let me write down the proof here. For a rational
V of it V, the Q trace
ZMVT is a modular form of a certain weight
under
the action
of the
modular group
SL2Z,
where
the module
transformation properties
are V and V1 minus
1 over t is equal to tk
is VM
vt. And we can see also that k is the weight of the module form, where k is the weight
of
the module and this property indicates that you see that ZMVT, or the module, transforms in a well-defined
matter
under module transformations. Let A be a finite dimensional associative algebra over an algebraically closed field K. Consider the following properties related to simple modules and the Jacobson radical JA of the algebra A. Prove that the Jacobson radical JA is the intersection of the annihilators of all simple A modules. So first, let me write down a proof. So let M1, M2, all the way to MM be a complete set of non-isomorphic simple A modules. And I'll define I is equal to, call it R is equal to 1 of N of A and N of Ni, where, let's see, where is, or denotes the annihilator of Mi in A. And we could also see that JA, the Jacobson radical, is a subset in I. We know that since JA, or the Jacobson radical annihilates
every simple A module. And then we could say, conversely, if A is an A, it enumerates every simple module MI. Thus, A lies in the intersection of all maximal left ideals of A, which implies that A is in J inside the Jacobson radical. So therefore, JA is equal to I. And we prove that the Jacobson radical JA is the intersection of the inner layers of all simple A modules. Let C and D be two chain complexes over a commutative ring R. So there are two chain complexes, and suppose FC goes to D and GC goes to D are two chain maps between C and D. Show that if F and G are homotopy equivalents, then they induce the same maps on homologies. That is, F is equal to G on H and C for all N. Well, let me write down a proof here. Let's say we have X be inside H of N, C be the homology class of a cycle. Let's say X is in Cn, where D and X is equal to 0. The induced map on homology is defined as, let's call this F is equal to F of Nx and G X is equal to G of Nx. We know that since F of Nx minus G of Nx equals D prime N plus 1 H of Nx plus H of N minus 1 Dn of X. And since we know that X is a cycle that is Dn of X is equal to 0, then F of N X minus G of Nx, meaning that F of N X and G of Nx differ by boundaries in Dn, is equal to D prime N plus 1 of Hn of X. So therefore, see that F X equals F of N X is equal to G of Nx is equal to G of X here, proving that see F is equal to G
on homology. Consider the vibration F to E to B, where F is the fiber, E is the total space, and B is the base space of the vibration. Assume that B and F are connected CW complexes, and let HFZ, HBZ, and HEZ denote the cohomology rings of F, B, and E with integer coefficients. Suppose B is equal to S squared, the 2 sphere, and F is equal to S1, the 1 sphere. Find the E2 page and use it to determine the cohomology of E. So I'm going to write what's given. So we know that B is equal to this 2 sphere, and F is equal to S1. So the cohomology groups are H, S squared, C, and Z in degrees 0 and 2 and 0 otherwise. We know that H is S1Z, where Z in degrees 0 and 1 and 0 otherwise. So we have E2 PQ is equal to H of P. That means I'm writing down the E2 page of the sequence. S2 HQ S1Z. So this is the E2 page of the sequence. So let me figure out what H2 0 0 is. So that would be H of O S2 Z is equal to Z. E2 0 1 is equal to H0 S2 of Z is equal to Z. E2 2 0 is equal to H2 S2 Z is equal to Z. Now we do E2 2 1 is equal to H2 S2 Z is equal to Z. And then finally we have E2 PQ is equal to 0 for all other PQ. So let me write and draw an E2 page. So basically we have Q is equal to 1 here, Q is equal to 0, P is equal to 0, P is equal to 1, and P is equal to 2. Like a line, or not exactly a matrix, but C, Z, 0, 0, and Z, Z. So here is, this shows the E2 page. Consider the theory T in a first order language L with an infinite set of axioms, and where each is a sentence in L. Let L be the language of linear orders with a single binary relation. Define a set of sentences T is equal to N, where each N states that there are at least N distinct elements in the linear order. So that means there exists an x1, x2, all the way to xn, where x1 is less than x2 is less than xn, all the way to xn. Prove that T is consistent. So let me write down a proof here. So let's consider the set of sentences T
t is equal to this, where each sentence n asserts that there are at least n elements in the linear order. Every finite subset of T is consistent since it describes a linear with a finite number of elements. So for any finite n, so we have the sentence of 1 to 2 all the way to sentence n can be satisfied by a linear order on n elements. So by the compactness theorem, you see that T is consistent.
Consider the axiomatic system of Zermato-Franco set theory, CF, which includes the axiom of choice, CFC. Prove that the axiom of choice implies the axiom of countable choice.
So let me write down a proof here. So let's call it AN, where N is inside the natural number, be a countable collection of non-empty sets. And now I can construct a set. So let's say construct a set X. And let me call this AN. So by the axiom of choice, there exists a function called f such that for every a in X, we see that f of a is in A. Since X is countable, I can enumerate X as AN and apply the axiom of choice to get a function f such that f of an is an an for each n, and therefore we can see that the axiom of choice implies the axiom of countable
choices. Let L be the first order language of groups, and consider the theory T of abelian groups in L. Prove that every model of the theory of abelian groups is elementary equivalent to the direct sum of the divisible abelian group and a torso abelian group. So first, let me write down the abelian group. Let me denote this. G is isomorphic to D. This directs the sum decomposition of T, where D is divisible and T is the torsion, where D is divisible and T is torsion. In the classification of abelian groups, a fundamental result in the theory of abelian group is that every group G can be decomposed into a direct sum of a divisible abelian group and torso abelian group. So let me write down a proof here. So basically I need to prove that every model of T is elementary equivalent to the direct sum of a divisible abelian group and a torso abelian group. So let's consider any abelian group G and decompose G. So we say that a group D is divisible if for every G in D and every positive integer n, then that means there exists in H such that H of n is equal to G. And let me also write down what the group T. So a group T is torsion if every element of T has a finite order. So for any abelian group G, decompose G into G is equal to G divisible, which can be decomposed into a direct sum of G of the torus. So where G div is divisible and G torus is torsion. And I can see that the decomposition is unique up to isomorphism. And since that the theory of abelian groups describes properties that are preserved under isomorphism, and the decomposition of the abelian group into a direct sum of a divisible group and torsion group is unique up to isomorphism, it follows that for any two models of T that are elementary equivalent to the direct sum of a divisible abelian group and torso abelian groups. Consider the space R with a standard topology, so that every analytic set, a set in the summation of 1, 1 is a continuous image of a Borel set in R. Let me write down a proof here. So a set A is analytic in the sum of 1, 1 if there exists a Borel set B, which is a subset in R, such that A is the projection of B onto the first coordinate, where A is equal to, call this a set XR. That means there exists a Y and R. We see XY is in B, which shows that every analytic set is a continuous image of a Borel set, since the projection map is continuous. And specifically, the projection is a continuous map from the space R to R, where B is a Borel to R. Let K equal Q square root of 13 be a quadratic field, where OK is the range of the integers of K for an element alpha is equal to X plus Y square root of 13 with X, Y, and Z. Find the norm of NQ quotient AQ of alpha. So let me write down the equation for the quadratic field that is given. So we have alpha is equal to X plus square root of D. And given the quadratic field, Q is equal to Q over times square root of A, where D is a square free integer, any element alpha in K, where X and Y are rational numbers. So first, let me write down what's given. We have alpha equal to X plus Y square root of 13. And let me write its conjugate of the quadratic field. So it's basically just X minus Y square root of 13. So let me find NK then we have X plus Y square root of 13 times X minus Y square root of 13. So I just plug into the norm. And then I can expand from here. So this would be X squared plus Y square root of 13 minus Y square root of 13 minus Y square root of 13 squared, and these will cancel. Now what we're left with is X squared minus Y square root of 2. So get NK Q is equal to X squared minus 13Y squared. And I can see that the norm is the integer since X and Y are integers. And this norm is particularly important since it connects elements of the quadratic field with solutions to a certain Diophantine equation, which is, so therefore we have X and K, the norm of KQ alpha is X squared minus 13Y squared. Let F of Z be a modular form of wave 3 for the module group SL2Z. Consider the heck operator T2, which acts on module forms of wave 3 as follows. T2FC is equal to the summation of A01 of F of AZ plus B over 2, where the sum is over integers A and B, such that A is in 0, 1, and B is adjusted accordingly. Given that F of Z satisfies the relation T2FZ is equal to F5 F of Z, Find the module inverse of the Heck operator T2 with respect to the module form F2. So the Heck operator T2 acts on f of z and produces another modular form. In this case, T2 maps f of z to 5fz, meaning that f of z is an eigenform of T2 with eigenvalue 5. So first, I will determine the module inverse. And to find the module inverse of T2, I need to find an operator inverse of T2. So write down T2, where T2 inverse of f of z equal to f of z. Now this would be one-fifth f of z. Since T2 f of z is equal to 5 f of z, the inverse operator. And I can see that the module inverse of T2 is an operator that scales the module form f of z by 1/5. And I can apply the inverse operator to this. So this would be T2 f of z is equal to 5 f of z. And the inverse operator effectively undergoes the scaling effect of T2. So this would be inverse of T2 of f of z is just 1/5 f of z. So basically, this would be the module inverse of the Heck operator T2 with respect to the module form f of z. Let f of z be a module form of weight 2 for the module group S of L to z. The associative L function of f of z is defined as LSF is equal to the summation n is equal to 1 to infinity of an and s, where an are the foreign coefficient of the module form f of z. Suppose f of z is a cusp form and satisfies the functional equation L s of s of f L 1 minus s of L, where we have the last ff is a gamma function related to the fc. Assume that last ss is equal to gamma s, gamma 2 minus s over pi s minus 1, and let ls denote the Riemann set of functions. Given that LSF is equal to ls, find the special value of LSF at s is equal to 2. So first, let me write down what's given. So we have LSF is equal to LS, and given that LSF is at s is equal to 2, this would be 2f L2. And then the Riemann set of function of S2 would be L2 is equal to pi over 2 over 6. And then let me also write down log of f s of s based on the formula. 2 minus s. So gamma s, gamma 2 minus s over pi s minus 1. And to confirm consistency with the functional equation using the gamma function here. So let me simplify from here. So this would be plug in s is equal to 2. This would be gamma 2, gamma 0 over pi to the 1. And then we have L2f is equal to pi squared over 6. And however, gamma 0 is not well defined since the gamma function has poles at non-positive integers. So the special value of LSF as s equal to 2 would be pi squared over 6. Consider the algebraic curve defined by the following conic section over the rational numbers. Q, c is equal to x squared plus 2y squared is equal to z squared. Find all the rational points x, y, and z on this curve. So first I can use the projective coordinates in the projective plane. So this would be c is x squared plus 2y squared is equal to 3z squared. And now let me use z is equal to 1 to find the doping equation. So this would just be x squared plus 2y squared is equal to 3. Now let me plug in y is equal to 1 here.
this would just be 2. 1 squared is equal to 3. X squared plus 2 is 3. So x squared is equal to 1. X is equal to plus or minus 1. So we have xy is equal to plus or minus 1 when c is equal to 1. Now let me do y is equal to 0 here. So we have x is equal to plus or minus 3, root 3, which is irrational, so there is no solution. So the answer would be, so all the rational points on this curve would be plus or minus 1, 1, 1, when c is equal to 1.
Consider a sequence of independent and identically distributed, or IID, random variables x of n, where x of n is a Bernoulli random variable with probability p. That is, x of n is a Bernoulli of p. Define the following events. An is the event that xn is equal to 1 for all n that is greater than or equal to 1. And let f of n be the natural filtration defined by f of n is equal to the sigma algebra x1, x2, all the way to xn, where sigma denotes the sigma algebra generated by the random variables x1, x2, all the way to xn. Prove that the event a is equal to the limit as n approaches infinity. An belongs to the sigma algebra f of n.
So let me write down a proof here. So let's define a as a is equal to the intersection of n is equal to 1 to infinity, an, where an is equal to x of n is equal to 1 for each n. The event an is clearly an f of n, since f of n is the sigma algebra generated by x1, x2, all the way to xn. And an is a function of xn. We see that the sigma algebra we have the sigma algebra generated by x of 1, n of 1, x2 so we have f of n is nested as f1 to f2 all the way to fn. Meaning that f of n is an f of n plus 1, f of n plus 2, all the way. Since we know that f of n is a subset, proper subset of f, subset of fk, for any k greater than or equal to k, an is an fk for all k greater than or equal to n. Thus, the union of A n is in Fk for every k, and consequently A is measurable with respect to F0 to the tail sigma algebra. Thus, A is in Fn for sufficiently large n. That is, A is in F of infinity.
Consider the stochastic process xt defined by the following stochastic differential equation. SdE is of dxt is equal to u dt plus sigma dwt, where wt is a standard Brownian motion and u and sigma are constants. Define a new process yt as yt is equal to e to the alpha xt, where alpha is a constant. Use Ito's lemma to find the stochastic differential equation for yt.
So first, let me write down the equation for the stochastic differential equation. So this would be its partial with respect to x of the constant u plus 1/2. Take its second partial derivative with respect to x of constant square of sigma squared dt plus the partial with respect to x of sigma of dwt. And f of xt is twice differentiable function. So f of x equals alpha of x so its partial derivative with respect of e to the ax, alpha of x, is just alpha e to the alpha x. And basically I'm finding the first partial derivative of f of x, and now I need to find the second partial derivative. So this would be so basically the partial derivative with respect to a alpha times e to the alpha x, and this is basically just alpha squared e to the alpha x. Now applying Ito's lemma, is I'm plugging in the partial derivative. Now I can simplify from here. And this would be the stochastic differential equation for the process yt is equal to e to the alpha xt. Consider the initial value problem for the scalar conservation law ut plus f of u x is equal to 0, where r, x is in r, and t is greater than 0, with the initial condition u x0 is equal to u0 x, where x is in r, where f of u is equal to u squared over 2 is a convex flux function. Find uxt using the Lax-Olenek formula. So first, let me write down the convex flux function. So it'd be ut plus u squared over 2 x is equal to 0, where x is in r, and 2 t is greater than 0, with the initial condition ux0 is equal to the absolute value of x using the Lax-Olenek formula. So uxt is equal to the min of y of x minus y squared over 2t plus the absolute value of y. So basically I need to minimize the expression with respect to y. So this would be and to find the minimizer of y, I would take the derivative of this with respect to y and set it to 0. Basically it'll be y is greater than or equal to 0, and dy is equal to squared over 2t plus y, and this would just be negative x minus y plus t plus 1. So now I have x minus y over t equal to 1, and I can find in terms of y, so y would be equal to x plus 1. So now I have y is equal to x minus t for y is greater than 0, and y is equal to x plus t for y is less than 0. So now I have two conditions for the minimizer. So now I can plug the values back into the expressions. So it would be y is equal to x minus t. So this would be this would be t squared over 2t plus x minus t, and this would be simplified to t over t plus x minus t, and for y is equal to x plus t, I'll do this one now. This would be t over 2 plus x plus t. Now let me write down u of xt if x is greater than or equal to t, simply if x is greater than x minus t. And this would be the minimizing value of y if, let's say, x is between negative t and t. And also back to here, I would determine which would give the minimum. And this is what u of t using the Olax formula.
Consider the differential equation x squared y prime prime plus x 1 minus x y prime minus y is equal to 0, where y of x is the unknown function. The equation has a regular singular point at x is equal to 0. Use the method of Frobenius to find a series solutions about the point x is equal to 0.
So first, let me write down the differential equation again. Now I would like to write down the series solutions where r is constant to be determined. So basically this is an assumption I'll write down here. Sum of n is equal to 0 of a n of x n plus r. Now let me write down y prime of x equal to of a n. This would be n plus r x n plus r minus 1. Basically I'm finding the derivative. And now let me do y prime prime x, and that would be the summation of a n n plus r minus 1 x n plus r minus 2. And now I could plug it back into the differential equations. So all these back in. So let's see, we got x squared a n of n plus r n plus r minus 1 x n plus r minus 2 plus the x 1 minus x over the sum a n n plus r x, and then we got this summation here. So a n x n plus r is equal to 0. Now let me simplify from here. So we have plus the summation n is equal to 0 infinity of a n n plus r x n plus r minus n is equal to r infinity a n n plus r x n plus r plus 1 minus n is equal to 0 of infinity of a n x n plus r. And now I can combine like terms to make this even simpler. So I have a n n plus r plus n plus r minus 1 plus n plus r minus a minus 1 n plus r minus 1 minus an. This would be x n plus r is equal to 0. And now I can find the integral equation, which comes from the coefficient of the lowest point of x. We have r times r minus 1 plus r minus 1 is equal to 0. And then simplifying from here, we get r squared minus r plus r minus 1 is equal to 0. See, these cancel. We have r squared is equal to r squared minus 1 is equal to 0. Add 1 to both sides. We get r squared is equal to, we get r squared minus 1, so therefore we can actually factor this out. R plus 1, r minus 1 is equal to 0. And now we have r1 is equal to 1, and r2 is equal to negative 1. So these are the roots. And using the roots, I can find the recurrence relations for the coefficients, an. So therefore the recurrence would be n plus n plus r minus 1 plus n plus r minus 1. And then this could be simplified is equal to, this would be equal to an minus 1 of n plus r minus 1. So here's the method of Frobenius to find the series solutions about the point x. And for n, the recurrence relation is obtained by the coefficient of each, or basically telling the coefficient of each power of x n plus r to be 0. Consider the function jy is equal to the integral of x1 to x2 of f of x, y prime dx, where y is equal to yx is the function to be determined, y prime is equal to dy dx, and f of x, y prime is a given function. Find the function yx that extremizes or minimizes or maximizes the functional jy. So basically I need to derive the formula called the Euler-Lagrange equation. And the Euler-Lagrange equation is derived by a small variation. So let me write that down. So we call this J of y plus epsilon. We take the integral of x1 to x2 of f of x, y plus epsilon n y plus y prime plus epsilon n prime dx. And basically, so I said the Euler-Lagrange equation is derived by a small variation n of x in the function y of x, leading to a new function y of x plus epsilon n of x, where epsilon is a small parameter. And basically, I just plug in y of x plus epsilon n of x into the functional j of y. So from here, this would be f of x, y plus epsilon n, y prime plus epsilon n prime is y f of x, y prime plus epsilon with its partial derivative with respect to y of n plus its partial derivative with respect to y prime of n prime plus 0 epsilon squared. So that's an approximation. So let me write down J. I'm going to put this as curly, as brackets. Y plus epsilon n is equal to the integral of x1 to x2 of f of x, y prime plus epsilon take its partial derivative again. So we have this as dx plus 0 epsilon squared. And now I could find the first variation of the functional. So let me write that down. So we wrote this as delta j is equal to derivative of its epsilon, j y plus epsilon n is equal to the integral of x1 to x2 of its partial with respect to y, and then its partial with respect to n dx. And this is the first variation of the functional, is the term linear in epsilon. So let me also write this down. So we have x1 and x2. The integral of x to x1 to 2 is equal to its partial derivative dx is equal to partial derivative with respect to y prime and minus the integral of x1 to x2 d dx of its partial derivative with respect to y prime times n dx. And with n prime is equal to dn dx is the way to eliminate the derivative of n by integrations by parts. So plugging into j, let me write down. So delta j is x1, x2, and we have its partial with respect to f, y minus d dx of its partial with respect to y prime times n dx plus also its partial with y prime n. And now let me write this again. So bx1 to x2 and for yx, to extremize the functional jy, the first variation of delta g must be 0 for all variations n of x, if n of x1 is equal to n of x2 is equal to 0. This would be it can be written as this. Since n of x is arbitrary, the integral must be 0 or integrand. So therefore, so it'd be partial with respect to y of the derivative with respect to x and its partial derivative with respect to y prime. And this is the Euler-Lagrange equation. So basically, we found the function y of x that extremizes the functional jy. Consider the matrix given by A is equal to 4, 2, 3, 2, 6, 1, and 3, 1, 5. Perform the LU decomposition of the matrix A, where A is equal to LU, and determine the matrices L lower triangular and U upper triangular. So first, let me write down the matrix A, which is LU and given. So L would be its lower triangular. So we would write this, it's a 3 by 3, so it'd be 1, 0, 0. We have 1, 2, 1 here, 1, 0 here, 1, 3, 1, 1, 3, 2, and 1. Let me also write down U. So it'll be U11, U212, and U13, 0, 0, 0, U22, and U23, and U33 over here. In this case, you know that U11 is 4 from the matrix, U of 12 is 2, and U of 13 is 3. And now let me find 1 to 1 here. And all I can just do is simply you do A to 1 divided by U11, which is just 2 over 4. And we get 0.5 or half. And let me figure out what U22 is by just doing A22 minus 121 times A12. So this would get 6 minus 0.05 times 2 is equal to 5. Now let me find L31. This would be A31 divided by U11. So it'd be 3/4 or 0.75. And now let me do U23. It'd be A23 minus L21 times A13. And this would be 1 minus 0.5 times 3. And that should give us negative, let me write down here, negative 0.05. And now L32. So it'll be A32 minus L31 times U12 over U22. This would be 1 minus 0.75 times 2 over 5. And that's just 0.1. And now A33 minus 131 times U13 minus 132 times U23. And this would give us, let's see, 5 minus 0.75 times 3 minus 0.01 times negative 0.5, which is equal to 2.1. So we figure out all the missing values. So I think I'll write it down here. So L, based on the values, would be 1, 0, 0. Then we have 0.05, 1, 0, 0.75, 0.1, 0. And then U here would be 4, 2, 3. Then we would have 0, 5, negative 0.5, 0, 0, 2.1. So let me write this as A is equal to LU in terms of the matrix. So A is equal to LU is equal to 1, 0, 0, 0.5, 1, 0, 0.75, 0.1, 1. And we have U here. So it'd be 4, 2, 3, 0, 5, negative 0.05, 0, 0, 2.1. And this is the LU decomposition of the matrix A. Consider the finite field G of 7 denoted as F3. Find the result of 3 plus 5, 6 times 4, and 2 plus 5 times 3 in F7. So first let me find the results of 3 plus 5. So that would just be 8. So it'll be 8 mod 7 is equal to 1. So 3 plus 5. Now let me find 6 times 4. That's just 24. So 24 mod 7 equals 3. And let me find 2 plus 5. But 7. So 7 mod 7 is equal to 0. Times 3 is 0. So 2 plus 5 times 3 in F7.
A particle of mass m is subject to a force F of RT is equal to negative kr, where r is the position vector of the particle, k is a positive constant, and t is the time. The particle is initially at position r0 is equal to rho and has an initial velocity fv0 is equal to vo. Determine the equation of motion of the particle using Newton's second law. So first let me write down Newton's second law.
So this would be the equation. And now, given the, let's plug in the given force. Should be a square up here. And now I can write this as a second order linear differential equations. So it would be dr squared plus dt squared plus k over mr is equal to 0. And then this would be dr squared plus d squared plus, and I would let w squared equal k over m. So the equation is really dr squared plus dt squared plus w squared r is equal to 0.
So this is the equation of motion of the particle using Newton's second law. Consider a particle of mass m moving one dimension under the influence of a potential Vx. The wave function xt of the particle is given by xt is equal to a e to the I kx minus wt, where a is a constant amplitude, k is the wave number, and w is the angular frequency. Determine the velocity of the particle according to the Brunswick theory.
So first, let me write down in the de Broglie theory. So first off would be vxt is equal to 1 over m. It's partial with respect to xt over x. And in the de Broglie theory, the velocity xt of a particle is given by the gradient of the phase s of xt of the wave function. Then let me write down the wave function. So it's equal to rxt e to the is ht over h, and the wave function with rxt is being the amplitude and sxt is the phase. So let me write down kx minus wt, and this is for the given wave function I. Identify the phase s of xt. So s of xt is we know that v of xt is equal to 1 over m ds t over respect to x. This would be 1m and then we get ck x minus wt, and this is just equal to 1 over n hk, and this is basically the velocity. So we really just v of xt is equal to p over m is equal to hk over m. And then since hk is equal to p, where p is the momentum of the particle.
Consider a system of n non-interacting distinguishable particles in thermal equilibrium at temperature T. Each particle can occur one of three possible entry levels. E0 is equal to 0, E1 is equal to epsilon, and E2 is equal to 2 epsilon, where epsilon is a positive constant. Find the partition function for a single particle. So first, let me write down the partition function for z.
So we note this as z is equal to the summation y of e to the negative b ei. So the partition function z for a single particle is where b is equal to 1 over kBt and ei are the energy levels of the particle. So expanding this forward, for the given energy levels, E0 is equal to 0, E1 is equal to epsilon, and E2 is equal to 2 epsilon. The partition function is, we'll see, this would be E to the B E0 plus E to the negative B E1 plus E to the negative B E2, which is equal to E to the negative B0 plus E to the negative B epsilon plus E to the negative B2 epsilon. So basically this would be simplified to Z is equal to 1 E to the negative B epsilon plus E negative 2 B epsilon. So this is the partition function for a single particle.
Consider a one-dimensional space exclusion process, SCP, on a finite lattice with L sites. The particles can move to adjacent sites with equal probability, but a particle can only move if the destination site is empty. Assume periodic boundary conditions, meaning the site L plus 1 is identified with site 1. The system is in a non-equilibrium steady state. Find the probability of finding a specific configuration in the steady state for a system with 2 particles and 3 sites. L is equal to 3. So let me write down the possible configurations. So since the system has 2 particle and 3 sites, let me write down. So we have 1, 1, 0. So this is particle at sites 1 and 2. Now this one would be 1, 0, 1. So this would be particles at sites 1 and 3. And then this one will be 0, 1, 1. And this would be particles at sites 2 and 3. And then the probability of finding a specific configuration would be 1 over the number of configurations. So basically it's just 1 over 3. So there are 3 possible configurations. So the probability f configurations is 1 over 3. Consider the following 2-dimensional quadratic function. F of xy is equal to 3x squared plus 2y plus 4y plus 6x plus 8y plus 5. Use the gradient descent method to find the minimum of the function f of xy and learning alpha is equal to 0.1. Perform 2 iterations of the gradient descent algorithm and find the updated values of x and y. So first off, I want to write down the formula for the gradient.
So it would be denote f of xy is equal to its partial derivative with respect to x and its partial derivative with respect to y. So this is the gradient. And now let me figure out, based on the
dimensional quadratic function, I'll take its partial derivative with respect to x of this function. So it would be 6x plus 4y plus 6. And then I'll take its partial derivative with respect to y, and we would get 4y plus 4x plus 8. And now let me write down its gradient computation. Basically just its partial. So it'd be 4y plus 4x plus 8. And now let me write down the gradient descent where alpha is the learning ratio. So it'd be x of n plus 1, y of n plus 1 is equal to x of n, y of n, minus alpha, take its gradient f of n, y of n is equal to 1. Given the starting point xo, yo is equal to 0, 0, and alpha is equal to 0.1, I can find the gradient at xo, yo is equal to 0, 0. First off, let me write down f of 0, 0 is just 6 times 0 plus 4 times 0 plus 6. And then we have 4 times 0 plus 4 times 0 plus 8. And that would be 6, 8. And now for x1, y1. This would just be 0 minus 0.6, 0 minus 0.8, so this would be the updated point of x1 and y1. And now let's find the gradient at x1, y1, which is negative 0.6 and negative 0.8. Let me do that again. And I can simplify it more. And I would get negative 0.8 and 2.4. So let's see, x2, y2 is equal to negative 0.6, negative 0.8, equal to negative 0.8, 2.4, which is negative 0.6 plus 0.08. Would just be equal to negative 0.52 and negative 0.104. So for x2, y2, the updated point would be negative 0.52 and negative 1.04. Consider the following system of nonlinear equations. F of 1 x, y is equal to x squared plus y squared minus 4 is equal to 0. And f of 2 of xy is equal to the sine of x minus y is equal to 0. Use the Newton-Raphson method to find an approximate solution to the system starting from the initial guess. X, O, Y, O is equal to 1.5 and 1.5 using one iteration. So first, let me write the system in vector form. Remember to note this as f of x is equal to f1 xy and f of 2 xy, and then plug in the equations. Is equal to 0, where we have and now I can use the Newton's Raphson method for systems of equations require the Jacobson matrix Jx, which is the matrix of partial derivative of f of x. So let me denote that. So partial with respect to x here. Also for y, for the and now let me take its partial derivative of each of the equation. So let's work with the first one. This would just be 2x. This would just be cosine of x. And we have this would just be 2y. And this would just be -1. So let me write down j of x. So j of x would be 2x cosine of x, 2y, and -1. Now this would be x of n plus 1 is equal to xn minus j inverse of x of n and f of xn. So let me start with the initial guess. So I'll write down. So for the initial guess, xo is equal to 1.5 and 1.5. We have f of x0 is equal to 1.5 squared plus 1.5 squared minus 4. We have sine of 1.5 minus 1.5 is equal to 4.5 minus 4. And this would be 0.99749 minus 1.5, which is equal to 0.5 and negative 5251. And now let me figure out j of x0 by plugging it back in. Be 2 times 1.5 cosine 1.5 to 1.5 and then -1. So this would just be 3 0.7074, 3 -1. And now I have to find the inverse of Jx, so inverse of the 2 by 2 matrix. And it's really just, the inverse would just be 1 over AD minus BC times D negative B negative CA. So therefore I'm going to use J x0 -1. So it would just be 1, 3 times -1 times minus 3 times 0.07074. And this would just be -1, -3, -0.7,
0.07074 and 3. And then this would equal 1 over negative 3.21222. And then this would be negative 1, negative 3, negative 0.07074, 3. When I give approximation of JXO, so it would be 0.3331139, 0.93418, 0.02203, and negative 0.93418. And now for x1 is equal to xo minus j of the inverse of xo, f of xo. So x1 would be 1.5 minus 0.3139. We have 0.02203, 0.93418, and negative 0.93418. And then we also have the 0.5 and negative 0.50251. So I'm going to give approximation here. It'll be 1.5 minus, and do some simplification here. And this would be approximately 1.93676 and 1.02887. So I used the Newton-Raphson method to find the approximate solution to the system, starting with the initial guess. And it is 1.93676 and 1.02887. Consider a type of parabolic partial differential of a one-dimensional heat. We have the partial of u, and t is xt is equal to alpha of partial squared of u xt over partial of x squared, where t represents the temperature distribution over time, x is the spatial coordinate, t is the time, and alpha is the thermal diffusivity constant given the domain x is between 0 and 1 and t is between 0 and t. The initial condition is given by u of x0 is equal to sine pi of x, and the boundary conditions are u of 0,2 is equal to u of 1t is equal to 0 for all t is greater than or equal to 0. Using a uniform grid with spatial step size delta x is equal to 0.2 and time step size delta t is equal to 0.01, find a numerical solution for the one-time steps and determine the stability condition for this scheme. So first, I would discretionize the spatial domain of the 0 to 1 and the time domain of 0 to 1 using finite differences. So first off, I would denote xi is equal to I delta x, where I is equal to 0, 1, all the way to n, and n we have Tn is equal to, let's call this n delta t, where n is equal to 1, 0, 1 all the way. And now I can write down the heat equation here. Which can be approximated using the explicit formula time. So it'll be uin plus 1 minus uin over delta t. And the heat equation can be approximated using the explicit formula time, central space, finite difference scheme. Let me also write down its partial squared xi tn, partial is x squared, and this is approximately uni plus 1 minus 2 ui squared plus ui minus 1 over n, and this would be delta x squared. So uin plus 1 minus uin over delta t is equal to alpha, and then we have uni plus 1 minus 2 uni plus uni minus 1 over delta x squared. And then I basically plugged into the heat equation. So rearranging to solve for uin plus 1, where I can denote lambda is equal to alpha delta t of x squared, delta x squared is the stability parameters. So let me write down uin plus 1 is equal to un plus lambda and uni plus 1 minus 2 uin plus uni minus 1, where alpha is equal to lambda is equal to alpha delta t over delta x squared is the stability parameter. And now for the initial condition, u of x0 is equal to sine pi of x, this would be u of x0 is equal to sine pi xi for initial condition, where u of x0 is equal to sine of pi x. And then now I can write down the boundary conditions. So un is equal to for all n, so this is the boundary condition, and now I can find the stability parameters when alpha is equal to 1, so I'll just plug it in. So based on the equation, I'll just rewrite it again. So when alpha is equal to 1, then lambda would be, this would just be 1 over 0.01 over 0.2 squared, and this is just equal to, it's just 0.01 over 0.04, and this is just 0.25. Now let me find u of ni for n is equal to 0 and 1. So let me write down u n I for n is equal to 0 and 1. So let me find n is equal to 0 first. So ui0 will just be sine of pi I over, where I is equal to 0, 1, 2, 3, 4, 5. Okay, and now I could plug in u00. 0. This would just be 0. U of 1, 0 would just be, I'll just approximate, is 0.5878. And then u of 2, 0 would just be 0.9 0.9511. U30 just be 0.9511. U4 would just would just be 0.5878. And also for U50 would just be 0. This about here would be a 5 up here. And now let me find out what n is equal to 1 now. So U11 is equal to U01 plus 0.25 over U0 minus U10 plus U00. So U11 would be approximately, I'm just going to plug it in, 0.5878 plus 0.25 times, let's see, times 0.9511 minus 2 times 0.5878 plus 0. So U11. I'm just going to simplify even further. 5878 plus 0.25 of negative 0.2245. And U11 would be approximately 0.53167. And now the 4 time, let me also write this down. The 4 time central space scheme is stable if lambda is less than or equal to 1.5 and say lambda is equal to 0.25. We see that therefore it satisfies the stability condition. So we see that U11 is approximately 0.53167. Consider the following linear time invariant LTI system described by the state space equations xt is equal to axt plus but, yt is equal to cxt, where the matrices A, B, and C are given by A is equal to 1, 2, 0, 0, 3, 4, 0, 0, 2, B is equal to 1, 0, 1, C and C is equal to 1, 0, 1. Determine whether the system is controllable using the controllability matrix approach. So first I'll need to determine if the system is controllable. So I'll find the controlling matrix of C first. So this would be C is equal to B, AB, A squared B. Let me just separate this a little bit out here. And now let me find AB first, since I already know what B is, which was given. Just make this bigger here. So that would just be 1, 4, 2. Now we find A squared B. And that is just really A times AB. It's really just taking A and then B, which is just 1, 4, 2. And then we get 9, 24. And now we could find C. It's just 1, 1, 9, 0, 4, 20, and 1, 2, 4. So this is the controllability matrix for C.
C. And now to check the controllability, I would need to determine if C is a full ring by finding the determinant of C. So let me denote determinant of C is equal to 119042124, and that would be 1 times 4 times 4 minus 2 times 20. And I would do minus 1 times 0 plus 9 times 0. So let me just still write this down for simplifying. So it'll be 4 times 4 minus 2 times 20 is equal to 16 minus 40 is just negative 24. So the determinant of C is negative 24. And since C is not equal to 0, which in that case, the matrix is full. So rank 3. So the system is controllable. You also write that down too. Consider a linear time invariant LTI system represented by the state space equation xt is equal to axt, where the matrix A is given by A is equal to negative 2, 1, 1, negative 3. Determine the stability of the system by examining the eigenvalues of the matrix A. So to determine the stability of the system, I need to find the eigenvalues of the matrix A. So first, I would need to find its characteristic equation by its determinant of A minus lambda I is equal to 0, where I is the identity matrix. So the determinant would be negative 2, 1, 1, negative 3 minus lambda 1, 0, 0, 1 is equal to the determinant 1, 1, negative 3 minus lambda and this would be, better put another bracket here, is equal to 0. So it would be negative 2 minus lambda. It's negative 3 minus lambda. So we get lambda squared plus 5 lambda plus 5 is equal to 0. And we can see that this is now in a quadratic equation. So now I could find lambda 1, 2. So using the quadratic formula, I could just plug it in. So we get that the roots are negative 5 plus square root of 5 over 2, and it's negative 5 minus 5 over 2. And since both eigenvalues have negative real parts, the system is asymptotically stable. Find the smallest integer n such that any graph with n vertices, when the edges are colored with two colors, red and blue, contains a monochromatic triangle, which is a triangle where all three edges are of the same color. So first off, the question is to determine the smallest number of vertices, n, such that no matter how I color the edges of a complete graph k of n using two colors, I will always end up with at least one monochromatic triangle. So let me consider a case here and give you all the possible. So let's say n is equal to 2. It's basically a complete graph with 2 that has no triangles. So let's try n is equal to 3. It's a complete graph with 3 vertices, which is a triangle and has only one triangle and in any two colorings of the edges. And at least one triangle will be monochromatic. Either all edges are red or blue. So let me do n is equal to 4. This is a complete graph, which K4 has 6 edges, and it is possible to color them in such a way that no monochromatic triangle. So an example would be a Peterson graph.
So let's do n is equal to 5. So K5 can be colored without producing a monochromatic triangle. And for n is equal to 6, it's any two coloring of the edges of K6 must contain a monochromatic triangle. So K6 would work. So I will write down a proof here to show this. So let's say consider any vertex V in K6. The vertex is connected to 5 other vertices, and by the pigeonhole principle, at least 3 of the edges must be the same color. So the subgraph formed by these 3 values or vertices connected by red edges must contain a red triangle, proving K6 cannot be colored without forming a monochromatic triangle. Given a set S is equal to 1, 2, 3, 4, 5, 6, and a collection of subset F is equal to S1, S2, S3, where S1 is equal to 1, 2, 3, S2 is equal to 3, 4, 5, and S3 is equal to 1, 5, 6. There are 2 colors, red and blue, which are the color of the elements. Find the 2 coloring of the sets that minimize the maximum discrepancy among all subsets in S. So first, my goal is to find a coloring of S such that the maximum discrepancy across all subset Si in F is minimized. So let me write down the discrepancy of a subset Si. So it would be discrepancy of Si is equal to, see, the number of red elements in Si minus number of blue elements in Si. So let me find all the elements. So color all elements of S red. So the discrepancy of S1 would just be 3. The discrepancy of S2 would be 3. The discrepancy of S3 is 3. And the maximum discrepancy would be 3. And now let me color 2, 4, 6 red and Let's do blue. 3 and 3, 5 blue. So the discrepancy of S1 would just be the absolute value of 2 minus 1, which is just 1. The discrepancy of S2 would be 1 minus 2, which is just negative 1, is just 1. The discrepancy of S3 would be 2 minus 1, which is just 1. And the maximum discrepancy would just be 1. Finally, I'm going to find the color of 1, 3, 5, red, and let's see, 2, 4, 6, blue. So the discrepancy of S1 is just 2 minus 1, which is just 1. The discrepancy of S2 would just be 1 minus negative 2, just negative 1 is just 1. The discrepancy of S3 would be 2 minus 1, which is 1, and the maximum discrepancy would just be 1 here. Consider the set S is equal to 1, 2, 3, 6, 9, 18 with partition order defined by divisibility. That is, for A, B is an S, A is less than or equal to B, if and only if A divides B. Draw the Hash diagram of this partially ordered set. So given the set elements S is equal to 1, 2, 3, 6, 9, 18, and the partition order, which is defined by divisibility, the Hash diagrams is drawn by placing elements A and B such that A is less than or equal to B is represented by a line from A to B with A below B, so only immediate successors cover relations are connected. So let me start with 1. So I'm going to draw a line here. And 1 is the smallest element, so it's at the bottom. And then let me draw a line here. Make this 2. And 3. And 2 and 3 both cover 1, since 1 divides 2 and 3. Now let me put a 6 here. And 6 covers 2 and 3, since 2 times 3 is 6. Then 9 would be up here, since 9 covers 3. And since 3 times 3 is equal to 9. And then another diagram up here. And then this would be 18 up here. 18 covers both 6 and 9, since 8 times 3 is equal to 18, and 9 times 2 is equal to 18. So this is the Hash diagram of this partially ordered set. Consider a social network represented by a directed graph. G is equal to VE, where V is equal to A, B, C, D, E is a set of nodes, and E is equal to A, B, AC, BD, CD, CE is a set of directed edges. Each edge UV has a PUV of transmitting influence from node U to node V. Assume the following properties: PAB is equal to 0.5, PAZ is equal to 0.4, and PBD is equal to 0.3, PCD is equal to 0.7, and PCE is equal to 0.6. Find the expected number of individuals influenced if the campaign starts at node A. To define the expected number of individuals when starting from node A, I sum the probabilities of influence propagations through all possible paths originating from A. So first, let me find the expected influence from A to B. We know that is just 0.5, and then the expected influence from A to C would be 0.4. Then so let's find BD. So if B is influenced with probability 0.5, the probability that D is influenced through B would be 0.3 times 0.5, which is just 0.15. Let me do probabilities. Influence to CD. So if C is influenced with probability 0.4, the probability that D is influenced through C would be 0.7 times 0.4, which is just 0.28. And now let me do C, probability CE. So the probability that E is influenced through C would be 0.6 times 0.4, and that would just be 0.24. Now I can find the expected number of influenced individuals starting from A. So basically just add them all up. So A1 plus 0.5 plus 0.4 plus 0.15 plus 0.28 plus 0.24. And A would be 2.57. So the expected number of individuals influenced if the campaign starts at node A is 2.57. Consider two measurement scales, a temperature scale TF in Fahrenheit and temperature scale TC in Celsius. The relationship between these two scales is given by the function TF is equal to FTC is equal to 9 over 5 TC plus 32. Prove that the function f of TC to TF is a homomorphism between the two measurement scales. Basically, a function f is a homomorphism between two algebraic structures if it preserves the structures of the operations, and for measurement scales it often means that it should preserve the difference between measurements. So first let me write the difference operation on the Celsius scale. So we denote delta TC is equal to TC2 minus TC1. And let me write down the difference of the Fahrenheit scale. Delta TF equal to TF2 minus TF1. And let me write down TC is equal to 9 over 5 TC plus 32. And I need to show that F preserves these differences. To do that, we do TF1 equal to FTC1 equal to 9 over 5 TC1 plus 32. Also TF2 is equal to FTC2 to 9/5 TC2 plus 32. And these are the two temperatures. TFF2 minus TFF1 is equal to 9 over 5 TC2 plus 32 minus 9/5 TC1 plus 32. And then we have TF is equal to TC2 minus TC1 is equal to 9/5 delta TC. And since the difference in Fahrenheit, the delta TF is directly proportional to the difference in Celsius, the delta TC by a constant factor of 9/5, F is a homomorphism that preserves the different structure between the two scales. Consider a simple undirected graph. G is equal to VE with n vertices and m edges. An independent set in G is a subset SV such that no two vertices in S are adjacent. That is, there is no edge connecting any two vertices in S. Using the probabilistic method, show that there exists an independent set in G with at least n squared over 4m vertices. So first, let me write down a proof here. So let each vertex
V be included in a subset. Independently. With probability P. And let's say we got expectation of the absolute value of S. That would be equal to Pn, where S is the expected number of vertices. So let X denote the number of edges in G with both endpoints in S. So for each edge, E is equal to UV, the probability that U and V are in S is P squared. So let me write down the expected number of edges. So it'd be EX is equal to the summation of UV inside E. We have the probability of US and VS is equal to the summation of UV in E of P squared is equal to P squared M. So this is the expected number of edges. And now to maximize the expected size of the independent set, I can differentiate the expression Pn minus P squared M with respect to P and set it to 0. So that would be d over dP is equal to Pn minus P squared M equal to N minus 2Pm is equal to 0. And then solving for P, we get P is equal to M2M. And then plugging P into the expression for E to the absolute value of S minus X. So we get N squared over 2M minus N squared over 4M is equal to N squared over 4M. And by the probabilistic model, I have shown that there exists an independent set in the graph G with at least n squared over 4m vertices. Let A be a subset of 1, 2, all the way to n, be a subset of the first n natural numbers. Roche's theorem states that if n is large enough, any subset A with positive density must contain a 3-term arithmetic progression, that is, numbers of the form A plus D, A plus 2D, with D is not equal to 0. Use a Behenge type construction. Show that there exists a subset A is a subset of 1, 2, all the way to n of size A, such that the absolute value A is greater than or equal to n times e to the negative c square root of log n for some constant c, and A contains no 3-term arithmetic progression. Let me write down a proof here. So let's consider the set of integer points. So let's call this x, x1, x2, all the way to xd. In the d-dimensional lattice ZD, where each coordinate xi satisfies, where we have xi is between 0 and m. We see that thus x lies within a hypercube with side length m. Consider only these, well, those points x that lie on the sphere. And let's define by the equation let's say we have the summation of I to 1 of d, where xi minus m minus 1 over 2 squared is equal to r squared, where r squared is a suitable radius. Chosen that r is an integer. Chosen that r is an integer, each point let's call this x is equal to x1, x2, all the way to xd, is then mapped to an integer. Hx, let's call it defined by, call it nx is equal to x1 plus x2m plus x3m squared x squared plus all the way to xd m d minus 1, which maps the point in ZD to a number in the set, say 1, 2 to MD. So let's say let's define A as the set of all numbers n of x obtained
from points X on the sphere. So we see that the number of integer lattice points on in ZD is known to be large for MD minus 1 as M grows. The size of A is approximately MD minus 1. And since M is equal to MD, you can figure out that the absolute value of A is equivalent to roughly 1 minus D. And we could choose D, so choosing D appropriately the absolute value of A is less than or equal to N times, let's call this, say, N to the negative C log N for some constant. C. The key property of the set A is that it avoids three-term arithmetic progression. And the proof of this relies on the geometry of the sphere, in that arithmetic progression would correspond to collinear points in the lattice, which are rare on a high dimensional sphere. So therefore, I have constructed a large subset with size alpha A is greater than or equal to n times the exponential of negative c of square root of log n that contains no three terms arithmetic progression, which provides a Benderet typed upper bound for subsets of integers, avoiding three-term arithmetic progressions. A company produces two types of products, P1 and P2. Each product requires a certain amount of raw materials and labor. The company wants to maximize its profit by determining the optimal number of units of each product to produce. Given the following constraints: profits per unit, P1 is equal to $40, P2 is equal to $30. Material and labor requirements: each unit of P1 requires 2 units of material and 3 hours of labor. Each unit of P2 requires 1 unit of material and 1 hour of labor. The company cannot produce a negative quantity of any product. Formulate the problem as a linear programming model and solve it to find the optimal production quantities P1 and P2 that maximizes the company's profit. So first, I would like to define the decision variable profits. Let me denote x1 here. It's the number of units of P1 produced. And let me note the x2 is the number
of units of P2 produced. And now let me find the company's objective is to maximize its profit. So I need to maximize Z is equal to 40x1 plus 3x squared, and Z is the total profit. And now let me construct. So here we'll have material constraint here. So it would be 2x1 plus x2 is less than or equal to 100. And then we have the labor constraint. So it would be 3x1 plus x2 is less than or equal to 90. And then a non-negativity constraint where it'll just be x1 is greater than or equal to 0 and x2 is greater than or equal to 0. So let me write this down. So I could just call it maximize Z is equal to 40 x1 plus 30 x2 subject to 2x1 plus x2 is less than or equal to 100. We have 3x1 plus x2 is less than or equal to 90, where x1 and x2 are greater than or equal to 0. And now I would like to set up a feasible region. So I'm going to draw a graph here. Let me denote this as feasible region as a title. And then this would be the x-axis. So this would be x1. So this would be units of P1. And also for x2, units of P2. And let me denote this as go up by 5s. So this would be 100 up here, 80, 60, 40, and then 20. And then across would have, let's say, go by 10s, 20, 30, 40, 50, 60, 10, 20, 30, 40, 50, 60. So first, I like to construct a material constraint. So based on the material constraints, so we have 2x1 plus x2 is equal to 100. So I say that it would be right there. This would be 2x1 plus x2 is less than or equal to 100. We see a point here would be 2060. And let me construct the labor constraint too. So that would be 3x1 plus x2 is equal to 90. So it will be roughly down here. Then 90 would be up here. And then this would be shaded in here. And over here would be its, to note this, 3x1 plus x2 is less than 90. And also the intercepts for the material constraint. So the intercept for the material constraint would be 50, 0, and 0, 100. And let's see the intercept for labor constraints would be 30, 0, and 0, 90. So this would be, let me just try to shoot this in right here. So this would be a point over here. This would be a point here, point up there, and a point there. And now I can see that the feasible region is a polygon, and the optimal solution will occur at one of its vertices. And the vertices can be solved by finding the systems of equation of each intersection. So let me do the intersection of two x1 plus x2 is equal to 100. And x1 is equal to 0. So it'll be 0, 90. So we have the intersection of 2x1 plus x2 is equal to 100. And 3x1 plus x2 is equal to 90 is 20, 60. Now we have the intersection. Let's see, the intersection of 3x2 plus x2 is equal to 90. And x1 should be at x1 here. So we see that would be x1 is equal to 0. So that would be 0, 90. So let me evaluate the function z is equal to 40x1 plus 30x2 at each corner. So the function would be z is equal to 40x1 plus 30x2 at each corner. So let's do it at 0, 90. So this would be z is equal to 40 times 0 plus 30 times 90, and that's just 2700. Let's do it at 2060 next. So we have 40 plus 20 plus 30 times 60. That would be 800 plus 1800, so that would be 2600. And at 30, 0, so z would just be 40, 30 plus 30, 0 is 1200. So we see that the optimal solution is x1 is equal to 0 and x2 is equal to 90. So these are the optimal solution. So the optimal solution is 0, 90. Since the maximum profit z is equal to 2700 is achieved by producing 0 units of P1 and 90 units of P2. So the company should produce 0 units of P1 and 90 units of P2 to maximize its profit under the given constraints. Let the domain Fp be a probability space, and let A and B be two events in F such that P of A is equal to 0.4 and P of B is equal to 0.5. Suppose that P intersects B is equal to 0.3. Determine whether the events A and B are independent. So to determine whether A and B are independent, given that A intersects B is equal to 0.3, I would find the product of their individual probabilities. So let me write probability of A intersects B is probability of A times probability of B if A and B are independent. So probability of A, B would be 0.4 times 0.5 is equal to 0.2. Then by definition of independence, so we see that probability of A
intersects B is 0.2. But given that probability that A intersects is equal to 3, which does not equal to probability A times probability B. So let's see. Given that probability A and B is equal to 3, which does not equal probability A, probability B. Therefore, events A and B are not equal.
Suppose that x1, x2, all the way to xn are independent and identically distributed, or IID random variables with mu2 invariance is equal to 9. Consider the sample mean x bar of n is equal to 1 over n the sigma of xi. What is the distribution of sigma bar n as n becomes large? So by the central limit theorem, as n becomes large, the distribution of the sample mean approaches a normal distribution mean and variance. So mathematically, it could be written as x of n goes to n mu variance squared over n, where d denotes the convergence in the distribution. So let me write this down. So bx converges to 2, 9 over n. So as n becomes large, the distribution of xn bar n approaches n to 9n. A factory operates with a set of machines, M1, M2, M3. The operator's manager needs to ensure that the system operates smoothly by making decisions based on the following logical conditions. If machine M is functioning, then machine M2 must also be functioning. Machine M3 can only function if both M1 and M2 are functioning. If machine M2 is not functioning, then machine M3 cannot function. Express the conditions in terms of logical propositions. So first, let me denote P as machine M1 is functioning. And then for Q, let me write machine M2 is functioning. And then for R, we see that machine M3 is functioning. And basically I'm letting P, Q, and R represent the proposition. So the logical conditions in this case are P goes to Q, which means that if M is functioning, then M2 must also be functioning. And let's do the next one. R, P, Q. This means that machine M3 can only function if both M1 and M2 are functioning. Let's do the last one. And this means that if M2 is not functioning, then M3 cannot function. These are the logical conditions. Given a set of sensors positioned in a two-dimensional plane and communication range for each sensor, find where each sensor is represented as a node and an edge exists between the two nodes, if the corresponding sensors are within each communication range. So, given the list of sensor coordinates, we have 2, 3, 5, 7, 8, 3, 10, 6, 10, 8, and we have the communication range is 5 units. So first, I would use the Euclidean distance between each pair of sensors, which is a distance formula. So first, let me write down the distance formula, and that's just x squared minus x1 squared plus y squared minus y1 squared. And basically, an edge exists between two sensors if their distance is less than or equal to the communication range, which is 5 units. So let me figure out each one. Let's do 5, 2 first. So this would equal 5. So an edge exists. Let's do
8 minus 2 plus 3 minus 3. It's just 36. This is 6. So that means there is no edge that's greater than 5. This would be roughly 8.54, and there is no edge. That means an edge exists here. Or no. This would be 125, which is 11.18. So that means there's no edge exists. Let's do 8 minus 5 plus 3 minus 7 squared. Here an edge exists. Let's do the next one. 6 minus 7 squared is just, let's see, 10 minus 5. So now it would be 26, so this would be roughly 5.10. So that means an edge does not exist here. Do the next one. Let's do 12 minus 5 squared plus 8 minus 7 squared. This would be square root of 50, which is just 7.07. So there is no edge for this one. So an edge exists. So this would be square root of 41, which is roughly 6.4. So there's no edge. And finally, let's do the last one. So it'd be 2.83. So an edge exists. So let me write down the nodes. Be A3, 10, 6, and 12, 8. And the edges would be 2, 3, minus 5, 7. Yeah, 5, 7 minus 8, 3. We also have A3 minus 10, 6, and then 10, 6 minus 12, 8. Suppose in a characteristic plane wave incident on a scatter in R cubed, the total field Ux at a point X is given by Ux is equal to U inc X plus U scat X, where U and inc X is the incident field and U scat is the scatter field. The scatter field satisfies the Helmholtz equation, the delta scatter field X plus K of X U of the scatter field X is equal to 0 in the exterior region of the scatter with the boundary conditions. The partial with scatter is equal to negative partial of the incident on the surface of the scatter where n is the outward normal. Formulate the integral equations for the scatter field, that is, use the combined field formulation or the boundary integral equation method. So I'll use the boundary integral equation using Green's theorem. The scatter fields of the scattered U scat can be expressed in terms of the boundary values and normal derivatives on S. And the boundary integral equation for the scatter field U scat is, so let me write this down. It's just the integral of S. Let's take its partial derivative, g x y. Make that again. So it'll be n y u scat of y minus g x y of partial u scat over n dsy. And this is the formula for the integral equation for the scatter field, where g of xy is the green function for the Helmholtz equation.
A researcher is studying the dynamics of a drug's concentration in the bloodstream over time. The concentration Ct of the drug is modeled by the differential equation dC over dt is equal to negative kCt plus p over v, where Ct is the concentration of the drug of time t, k is the elimination rate constant per hour, d is the dose of the drug administered in milligrams, and v is the volume of the distribution in liters. Given that the drug is administered as a single dose, d is equal to 500 milligrams, the elimination rate constant k is equal to 0.2 per hour, and the volume of the distribution is v is equal to 50 liters. Find the general solution of c of t. So first, the differential equation is the first linear order non-homogeneous differential equation. First, I would find the complementary homogeneous solution, and then a particular solution. So first, I write down dC over dt is equal to negative k ct plus dv. And then I would find a particular solution. So it'd be cpt is equal to cp, where dCp over dt is equal to 0. So basically, to find a particular solution, I would guess a constant. So getting Cp by itself, we get d over kV. And then I would combine a homogeneous and a particular solution. So here would be Ct is equal to Ce negative Kt plus d over kV. And then the initial condition is C0 is equal to 0. So C0 is equal to Ck0 plus d over kV. So 0 is equal to C plus d over kV, and then solving for c, I get negative d over kV, and then ct is equal to negative d over kV e to the negative kt plus d over kV, and then I would get ct is equal to d over kV 1 minus e to the negative kt. And there we go. Consider a simple gene regulatory network where a gene G can be either in an on state or off state. The gene is regulated by a transcription factor T, which can bind to the promoter region of G and activate its expression. The dynamic of the gene expression can be modeled by the following set of differential equations. So we have these two differential equations, the derivative g of n alpha t 1 minus g of n minus b times g of n, and dt over dt is equal to t times g of on minus delta t, where g of ont is the probability that gene G is on the on state at time t, t of t is the concentration of the transcription factor at time t, alpha is the rate of the activation of the gene by the transcription factor, beta is the rate of the activation representation of the gene, gamma is the rate of production of the transcription factor due to the gene being on, and delta is the degradation rate of the transcription factor. Determine the steady state value on G and T for the G regulatory work. So first, I will need to find the steady state values in itself, the time derivatives. So first, so denote this as dgon over dt is equal to 0. And dt over dt is equal to 0. And now I could write gon is equal to 0 is equal to alpha times t 1 minus g on minus beta times g on. Rearranging to solve for g of o n, I could use alpha times t times 1 minus g on is equal to beta times g on. So alpha times t is equal to alpha times t plus b times gon. So gon would be alpha over t over alpha times t plus beta. We found the first one. Now we have to find t. Let me
just arrange this, set to 0, and then let me solve this for t. Basically, I can just arrange it to solve for t. So t would be r times alpha times t over alpha times t plus beta over delta.
Consider Einstein's field equation in general relativity. RUV minus 1/2 GUV is equal to 8 pi g over C4 TUV, where RUV is the Ricci curvature tensor, GUV is the metric tensor, R is the Ricci scalar, TVUV is the stress energy tensor, G is the gravitational constant, and C is the speed of light. The action corresponding to Einstein's theory of gravitation is given by S equal to the integral of C to the 4 16 pi g r plus lk times square root of negative g d for x, where r is the Ricci scalar, lm is the Lagrange density for the matter fields, g is the determinant of the metric tensor, GUV, and d for k, x is the volume element in space time. Using Noether's theorem, derive the conserved current associated with diamorphism, coordinate invariance in general relativity. The first law of Noether's theorem states that every continuous symmetry of the action S of a physical system corresponds to a conserved quantity in the context of general relativity, and the relevant symmetry is diamorphism invariance of the action where arbitrary smooth coordinate transformations. So first, let me write down, consider a infinite coordinate transformation. So let's denote this as x. Where epsilon mu x is an infinitesimal vector field under this transformation. That matrix tensor GUV changes as to where delta u denotes the covariant derivative with respect to the metric GUV. So let me also write down integral of minus GUV plus the total derivative times g d4x. And the action as changes under this transformation, using that the variations of the action must vanish for any arbitrary epsilon mu of x. So this would be, and this coordinate yields Einstein's field equations. However, for Noether's theorem, I focus on the associative conserved current. So in this case, I would write this as Ju is equal to delta L, or delta V G of alpha B, and I would note this as delta epsilon mu, and this is the conserved current J mu associated with diamorphism invariance, which is the first term involves the canonical energy momentum tensor, while the second term represents the divergence of a superpotential. Now let me write down the conserved current Ju. And here it is. And this is the conserved current Ju, is where it represents the energy momentum conservation in curved spacetime, where the covariant divergence of the stress energy tension vanishes at u of TUV is equal to 0. So it vanishes at. Consider the direct equation for a spin minus a half particle in a curved spacetime with metric GUV is a direct equation in curved spacetime is given by I gamma u direction of u of the wave equals to m times the wave, where wave is the spinor field, m is the mass of the particle, gamma u is the curved spacetime in gamma matrices, satisfying gamma u, gamma v equals 2gvi on, and u is the spinal covariant derivative defined by u, wavelength of u, partial u of the wavelength of partial u wave plus 1 for its w a u a b, and t gamma atb, where WAB is the spin connection. Show that the direct operation D is equal to I gamma U del U is formally self-adjoint on the Hilbert space of square integral spinors. H is equal to L square ms, where m is the spacetime manifold and s is the spin bundle.
So first I need to show that the direct operator D equals I gamma U V is formally self-adjoint. So basically I need to prove So first let me do the inner product space of this. In the inner product of the space of the squares integral spinors, where we have this is the direct adjoints and of the wave, and square root of negative g is the determinant of the metric. So let me consider the inner product. Again, once more. Integration by parts, and using the fact that the spinal covariant derivative is a covariant derivative which satisfies, we have delta u of square root of negative g vu is equal to 0 for any vector field. And since we have and therefore we see that D is formally self-adjoint.
Evaluate the integral I is equal to the integral of 0 to pi over 2 sine of x dx using numerical approximation and trapezoidal rule with n is equal to 4 intervals. So first let me write down the trapezoidal rule.
Plus 2. This is the trapezoidal rule approximation what I'm writing down. And what's given is that we have h is equal to b minus a over n. We have x of I is equal to a plus ih. We have f of x is equal to sine of x over x. And a is equal to 0, b is equal to a half. So that means h is equal to pi over 2 minus 0 over n is equal to pi over 2n. And now let me plug in n is equal to 4 So h is equal to pi over 8. We have x 0, 0. x1 is equal to pi over 8. x2 is equal to pi over 4. x3 is equal to 3 pi over 8. And x4 is equal to pi over 2. And now let me figure out f of x0. And that's just the limit as x goes 0 of sine of x over x. It's just 1. Now I do f of x1. That's just sine of pi over 8 over pi over 8. And that's just 8 sine of pi over 8 over pi. So f of x1 is about 0.982. And I'll do f of x2. That's just sine of pi over 4 over pi over 4. So this would just be 4 sine pi over 4 over pi. And this should be equal to 4 square root of 2 over 2 over pi. Is equal to 2 square root of 2 over pi is 0.9. And f of x3, do sine of pi, 3 pi over 8. And then this would be 3 pi over a2. And this would be 8 sine 3 pi over 8 over 3 pi, which is just roughly 0.757. And now let me do f of x4. So it would just be sine of pi over 2 over pi over 2, which is just 2 over pi. And this is just approximately 0.636. And now I can plug it in using the trapezoidal rule formula. Simplifying from here. So T4 would equal pi times 6.914 over 16, which is roughly 1.358.
Consider the following boundary value problem for the one-dimensional Poisson equation. Negative square ux over x squared is equal to f of x, where x is in 0, 1 with boundary conditions u0 is equal to 0 and u1 is equal to 0. Where f of x is a given continuous function to scrutinize the interval 0, 1 and n equally subintervals with grid points xi equals I times h, for I is equal to 1, 2, all the way to n. Where h of in is the grid spacing, and use the central difference approximation for the second derivative to derive the finite difference equations at each interior grid point x of I. The first point, I want to write down the grid points.
Where I is equal to 0, 1, all the way to, with h is equal to in. Now the second part, the derivative of xi can be approximated by the central difference. So it would be negative u plus I minus 2u I plus u I minus 1 over h squared minus f of x I, where I is 1, 2, all the way to n minus 1. And basically this is the finite difference equation.
Consider a two-period binomial model for a stock. The current price of the stock is SO is equal to 100. In each period, the stock can either move up by a factor, mu 1/2, or down by a factor d is equal to 0.8. The risk-free interest rate per period is R is equal to 0.5 or 5%. I want to price an American call option on the stock with a strike price, K is equal to 105, which can be exercised at any time before or at expiration after 2 periods. What is the risk-neutral probability of the stock moving up and down? So first, let me write down the formula for the stock risk-neutral probability for P. And that would be P is equal to ER minus D for U minus D. So we have ER is approximately E to the 0.05. So that'd be 1.5127. Basically, I have to find ER. And now I could just plug back in the numbers. This would be 1.2 minus 0.8. And this is just 0.25127 over 0.4. And this is approximately 0.6282. And this is when it's moving up. And then now to find for moving down, I would just do 1 minus P. So really it's just 1 minus 0.6282. It's just 0.3718. So this is moving down. Consider a financial market where the stock price ST follows a jump diffusion process, which is a type of Levy process. The dynamics of the stock price are given by the stochastic differential equation, or SDE. D of ST is equal to ST times mu dt plus sigma dWt plus JT minus 1 times D of U mu t, where mu is the drift term, the sigma is the volatility, Wt is the standard Brownian motion, Nt is the Poisson process with intensity lambda, and Jt is the random jump size, which is independent of Nt and Wt, and is a log normally distributed, such that log of Jt is normally of gamma epsilon squared. What is the SDE for the process log of St? So first off, with log of St, I would apply Ito's lemma. So let me write down Ito's lemma. And this is Ito's lemma. And now I'll apply the Ito's lemma into the formula based on the formula. So dst is equal to st u dt plus variance dwt plus jt minus 1 over dnt. And now let me do dxt is equal to 1 over st dst minus 1/2 1 over st squared of dst squared. So plugging dst, I get dxt is equal to 1 over st of st u dt plus this would be 1/2 times 1 over st squared. Take the variance squared. And now I can just simplify more. And then I could find the SDE of xi, which is equal to log of st. So take its, so it'll be d log st is equal to mu times 1/2 and this is this SDE for the process log of ST. I am asked to price an Asian call option using Monte Carlo simulation. The payoff of the Asian call option depends on the average price of the underlying asset over a certain period rather than the price at a specific maturity date. The underlying asset follows the geometric Brownian motion GBM with dynamics dst is equal to mu st dt plus the sigma st dwt, where st is the asset price at time t, We have mu is the drift rate, the sigma is the volatility, and WT is the standard Weiner processes. The payoff of the agent call option is given by the payoff is equal to the max of 1 of n of the summation of I is equal to 1 of n STI minus K10, where STI is the asset price at each time TI. Simulate the asset price paths using the Monte Carlo simulation in the given GBM models. So first off, let me write down what's given. And now for a discrete time approximation, I'll write down SI plus 1 is equal to STI, and then this would be the E to the R negative variance squared TT delta T plus sigma DT ZI, and ZI is independent standard normal random variable. And for a discrete time approximation with time steps delta t is equal to t over n, the GBM can be stimulated. So let me write down the steps to show you how it goes. So steps, so set SO is equal to 100. So for each simulated path, generate a sequence of n random variables. Let's denote this as ZI is this, and then generate the asset prices. We call them S1, ST1, ST2, all the way to STN for each path. Consider a credit default swap, CDs, on a computer bond issued by a company. The CDs is a financial derivative that provides protection against the default of the company. The CDs contract has the following characteristics. Notional amount is 10 million. The maturity is 5 years. Annual premium is 150 basis points, BPS. The recovery rate is 40%. Risk-free interest rate is 3% per annum, assumed constant. Default intensity is a hazard rate is lambda is equal to 0.02 per annum, assumed constant. Payment frequency quarterly. Find the expected present value of the premium leg of the CDs, which involve the payments made by the protection buyer. So first, let me write down the formula for the quarterly premium payment amount. Premium payment would be notional times annual premium over the payment frequency. So this would just be equal to the premium payment would just be, so we get 10 million times 0.015, and that's over 4, and that would be 37,500. And I'm going to write down the quantity payment I at time. So I denote this as TI is equal to I over 4. And the payments are made quarterly, so I need to discount each payment by both the risk-free rate and the default intensity. So let me also write down the discount factor, or the risk-free rate is just e to the negative RTI, and its survival probability. So there is no default
up to ti, and that would just be e to the negative lambda ti. And now let me write down the total expected present value of the premium. So that would be EPV premium would just be the summation of I is equal to 1 of 20 of e to the r plus lambda ti times the premium payout. I'm just going to plug in r is equal to 3, lambda is equal to 2, and the premium payment is $37,500. So that would be so e to the negative 25 is roughly 0.7788. So this would be 1 minus 0.7788 minus 0.9875. And that would be 17.696. So to find the EPV premium, I would just do 37,500 times 17.696. That would give 663,600. A portfolio with 3 assets of the historic annual return variances and covariance of the assets are given. So we have the assets A, B, and C with an expected return of mu I is 8%, 12%, and 6%, and the variance is I is 0.04, 0.09, and 0.01. And the covariance matrix between the assets is covariance of AB is equal to 0.002, covariance of AC is equal to 0.001, covariance of BC is equal to 0.0015. Find the variance of the portfolio consisting of these 3 assets with weights WI is equal to 0.4, WB is equal to 0.4, and WC is equal to 0.2. So first off, I'd like to write the portfolio variance using the formula. So now we just plug it in. And then simplifying from here, we get 0.02248. And now taking the square root, we could do square root of this. And we get that OP is roughly 14.99%.
So the standard deviation or the vitality of the portfolio is 14.99%. The whole white model is given by DRT is equal to data T dt plus sigma T RT dt plus sigma T dWt, where RT is the short rate, data T is the deterministic function of time, sigma T of vitality of the short rate, and Wt is the standard Brownian motion. Set up the whole white model and determine the parameter data T and sigma T that best fits the market swap rate and prices. So the whole white model of the short rate dynamics would be where alpha is the mean reversion speed. This would be the constant. Data T is equal to data. And this would be the constant. So we have P0T is equal to 1 minus e to the a t over alpha t, e to the negative data t times 1 minus and the price of the swap can be calculated using the whole white model by solving the term structure of interest rate under the model for a swap with maturity T and tenor T. And the swap rate K could match the following equation, where P of 0T is the price of a zero coupon bond at time T with maturity T. To best fit the model to market data, I will use the numerical optimization to minimize the difference between the theoretical swap prices and the observed market prices, which can be done using the least square method. I am a risk analyst at a financial institution assessing the credit risk of a portfolio of corporate bonds. The portfolio consists of bonds with different credit ratings, and I am using a credit risk model to estimate the potential losses due to the defaults given the portfolio details. Bond A value is 10 million. Default intensity rate is lambda A is equal to 0.02 per year. Bond B is a value of 15 million and default intensity rate for lambda B is 0.03 per year. Assuming that the default intensity are assumed to be constant and independent, and the portfolio is assessed for of one year horizon. Estimate the expected loss for each bond using the Poisson default model. So first, let me write down the model for the expected loss for bonds under the Poisson default. So note, expected loss is equal to value times default. Well, that's just default probability. And the default probability for a Poisson process over a time period 1 year. So let me write down the default for a probability. So just 1 minus e to the negative lambda t, where lambda is the default intensity rate and t is the time period, which is 1 year. So let me work with bond A. The probability default would just be 1 minus e to the negative 0.02 times 1, which is just 1.09802, which is just 0.0198. And I'll just multiply 10 million times 0.0198, and that's 198,000. And now let me find bond B. And that is just 1 minus 0.7904, which is 0.0296. So ELB would just be 15 million times 0.0296,
So ELB would just be 444,000.
I am a risk manager at a financial institution responsible for conducting stress tests on the company's trading portfolio, given the portfolio's details. So the equity is $100 million, the bonds is $50 million, the derivative is $30 million. For stress scenarios, the equity market crash drops 30% in equity prices. For a bond yield spike, a 200 basis points increase in bond yields. For derivative volatility shock, a 50% increase is implied volatility for derivatives. Calculate the loss for each asset class under the given stress scenarios. Assume the following sensitivities. So the equalities is the portfolio's beta is 1.2 and the equity price drop affects the portfolio proportionally. And the bonds, the duration of the bond portfolio is 5 years, and the change in bond values can be approximated using the duration. For the derivatives, the portfolio's Vega sensitivity to volatility is 1 million, and the change in the derivative value is proportional to the change in applied volatility. So first, let me find equities. So the loss equities equals the equity value times price drop times beta. So the loss equities is 100 million times 0.30 times 1.2. The loss equation is 36 million. Let's do bonds. Be its bond value times change in yield times duration. So lost bonds would be 50 million times 0.2 times 0. Where we get 0.5, where we get 5, and this is just 5 million. And for derivatives, so the loss derivatives would just be its Vega times change in volatility. So loss derivatives would just be 1 million times 0.5, so that's 500,000. So the loss derivatives is 500,000. For the loss equation is 36 million, loss bonds is 5 million, and the loss derivative is 500,000. I am a portfolio manager at a financial institution and tasked with optimizing a portfolio of assets to achieve the best trade-off between risk and return. The portfolio has 3 assets, A, B, and C, and historic annual return and standard deviations are given for each asset, as well as the correlation matrix among the assets. So we have assets A, B, and C, and the expected returns are 8%, 12%, 10%, and standard deviations are 15%, 20%, and 25%. And we have a correlation matrix of 1, 0.6, 0.4, 0.6, 1, 0.5, 0.4, 0.5, and 1. Determine the optimal asset weights that maximize the portfolio's returns for a given level of risk. Specifically, solve for the weights that maximize the Sharpe ratio of the portfolio, assuming a risk-free rate of 3%. So first, let me write down the formula for the Sharpe ratio. So this would just be RP minus RF over sigma P, where we have RP is the portfolio return. We have RF
is the risk-free rate, and sigma p is the portfolio standard deviation. And now I would like to also maximize the Sharpe ratio. So I need to solve the optimal problem. So let's say maximize WTR minus RF over the square root of WT of the sigma of W, where W is the vector of portfolio weights, and we also have R, which is the vector of expected returns, and also the sigma, which is the covariance matrix of assets returns. Now I'm going to write down the covariance matrix for this, and this would be equal to 0.15 squared, 0.15, 0.0, that's 0.6, 0.15, 0.25, 0.4. This would over here would be 0.15, 0.20, and 0.6. Also have 0.20 over here squared, and then 0.20, 0.25, and 0.50. And up here it would be 0.15, 0.25, 0.40, and the covariance matrix can be solved from the stands and deviations and the correlation matrix. So simplifying from here, I can simplify to 0.225, 0.0180, 0.0150, 0.0180, 0.0400, 0.0250, 0.0150, 0.0250, and 0.0625. And I can use the numerical operation techniques, the quadratic programming, to find the optimal weights W that maximizes the Sharpe ratio, subject to the constraints RTW is equal to 1, where W is greater than or equal to 0.
Alright guys, thank you so much for watching this video. Those were all the math courses that I showed with you from Rutgers University in New Brunswick. And I believe wherever you go, it's not just Rutgers, but any school, including Ivy Leagues, they teach the same material as in Rutgers. So that's all the mathematics there is in the world, I believe. So I hope you learned a lot from this and benefit from it. So I hope you enjoyed this video. Please subscribe, and I'll see you in the next video.